Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Good morning, ladies and gentlemen, and welcome to the National Research Center. Please rise for the national anthem of the Arab Republic of Egypt. Distinguished professor and colleagues, ladies and gentlemen, I am Dr. Hind Izzat, Secretary of the 4th Hybrid International Conference on the Molecular Modeling and Spectroscopy. On the behalf of the organizing committee of the conference, I have the pleasure to welcome Professor Hussein Darwish, Acting President of the National Research Center, Professor Medhat Ibrahim, Conference Chairperson, Professor Osama Osman, and Professor Hanan Al-Hayes, Conference persons. Professor Amr Abdelghani, the conference coordinator. And equally, I have the pleasure and the honor to welcome you all. Distinguished professors and colleagues, ladies and gentlemen, it's a pleasure and honor for me to address this assembly of eminent scientists and experts from different disciplines gathered to lay the ground of the 4th Hybrid International Conference on Molecular Modeling and Spectroscopy. First of all, I wish to express my thanks and facilitation to Molecular Modeling and Spectroscopy Group in the National Research Center for organizing this important event and for the hard work demonstrated in putting together different ideas and experiences into a comprehensive and coherent Congress program. Whether we are trying to address renewable energy, biotechnology, climate change, or disease surveillance, we need scientists with a clever vision and a commitment to work together to find solutions. Science has the potential to significantly impact all three dimensions of sustainable development: economic, social, and environmental. The international community must consciously and deliberately work to ensure that advances in science and technology have positive effects towards that end. Based upon this consideration, you are welcome to participate in this conference to integrate both basic and technical sciences to bridge the gap toward building the new Egypt based on science and technology. Distinguished professors and colleagues, before concluding this talk, let me take this moment to extend again my wholehearted appreciation to the organizers of this important Congress. I once again welcome you all and look forward to open discussions and concert and practical outcomes. Let's now start our opening ceremony by cordially inviting Mr. Magdi Sabe, Head of Bina Charity for Sustainable Development, to give his speech.
Welcome all of you in the 4th Hybrid International Conference on Molecular Modeling and Spectroscopy. I am Magdi Sabik, the head of Bina Charity for Sustainable Development. Ladies and gentlemen, dear audiences, it gives me great pleasure to welcome all of you in the 4th Hybrid International Conference on Molecular Modeling and Spectroscopy. We are a new charity organization working in the field of sustainable development. We are just starting our world since a year. We do believe that science could solve problems, especially for developing countries. We are willing to collaborate with universities and research institutes for environmental protection, waste management, and human resources development to sustain our resources in Egypt. In this conference, we hope for the first time that charity organizations could be part of the scientific community through continuous training programs. This is why we participate in society engagement programs as well as public awareness. We do believe that science plays the key role in sustainable development, and that all the society members must push the society toward scientific solutions. In this sense, a session will be conducted to present, in general, the civil society's major role in sustainable development with some highlights on the role of Bina charity in sustainable development in Calliope Governorate. To carry out these important issues, one must go through a general introduction for sustainable development, then talk about the sustainable development strategy in Egypt, demonstrating both the prospects and challenges. Finally, we wish you a successful conference and willing to receive your valuable recommendations that will be useful for our society. Thank you. Wish you all successful conference. Welcome all of you in the fourth hybrid.
Thank you, Mr. Magdi Sabit, for your speech. And now I heartily invite Professor Medhat Ibrahim, former Dean of the Physics Research Institute, to give his speech.
بسم الله الرحمن الرحيم. بيسعدني ويشرفني أن أرحب بحضراتكم جميعا في رحاب المركز القومي للبحوث. Molecular modeling is a class of computational approaches used to model or mimic the behavior of molecules. The common feature of the molecular modeling methods is at the atomistic level description of the molecular system. On the other hand, spectroscopy is a tool for studying the structure of atoms and molecules. It covers a wide range of application in physics, chemistry, biology, and astronomy. Molecular Spectroscopy and the Modeling Unit at Spectroscopy Department, National Research Center, Egypt, is providing professional technical consultation and designing molecular models for environmental reactions and electronic properties of matter. During the last 3 years, the unit launched the conference on the molecular modeling and molecular spectroscopy. The aim of the conference is to investigate innovative applications and latest research in the area of molecular modeling and molecular spectroscopy. It will also cover issues in quantum mechanical molecular modeling together with molecular spectroscopy for creating a stage to exchange the latest research results and sharing the advanced research methods. As a typical feature of the conference, it covers 2 main topics, namely the molecular modeling and computational method for environmental interactions, also for molecular and biomolecular spectroscopy. Molecular spectroscopy also for some systems, including material science, biological systems, surface and interfaces, earth and environmental science, and chemical analysis. Actually, during the preparation of this conference, we lost one of our greatest professors in not only the National Research Center, but also in Egypt. This is Professor Ahmed Abdurrahman Fakhri. This is why in this conference, we are going to dedicate this conference to the soul of Professor Ahmed Fakhri. Let me introduce in a couple of minutes a short introduction about Professor Fakhri.
In the memory of Professor Ahmed Fakhri. Professor Fakhri graduated from Faculty of Science, Alexandria University in 1960. He was granted PhD scholarship to the Soviet Union from 1961 to 1966 in Moscow State University. He joined Geological Survey Authority as researcher from 1966 to 1967. He was then appointed as a researcher in Spectroscopy Department, National Research Center in 1967. In 1979, he became Professor of Applied Spectroscopy. He was head of Spectroscopy Department from 1984 to 1990, and head of Physics Division from 1983 to 1985. He was a member of the Technical Office at the National Research Center from 1988 to 1992 and head of International Relations Office at the National Research Center from 1994 to 1998. He was appointed as Vice President of the National Research Center for Scientific Affairs and International Relations from 1996 to 1998. He was in 10 scientific missions outside Egypt in different laboratories in the fields of atomic and applied spectroscopy. He supervised about 12 theses, worked as a member and PI in 7 research projects and published more than 80 research papers in national and international journals. He is a member in many societies, communities and committees in Egypt. His research interests include atomic emission spectroscopy for minerals, rocks and different geological samples as well as environmental samples. The Molecular Spectroscopy and Modeling Unit was established by him. Also, our conference is also established by him. This year Professor Fakhri passed away, so that this conference is dedicated to his memory. This conference is dedicated to the soul of Professor Ahmed Fakhri.
So let me say a couple of words in Arabic. في الواقع احنا بنفتقد استاذنا الاستاذ الدكتور احمد عبد الرحمن فخري. احنا كلنا كنا بنشحن بطارية الامل من استاذنا الاستاذ الدكتور احمد فخري. اسمحوا لي حضراتكم نقف دي احداث ونقرأ الفاتحة على روحه. Thank you very much to all of you. I ask Professor Amr Abdel Ghani, the head of the National Committee of Physics at the Academy of Scientific Research and Technology, to give a recognition award to Mr. Nazar, the son of Professor Ahmed Fakhri. Please, Mr. Nazar. Actually, Professor Fakhri was the founder of this conference, and he's also the founder of the unit of molecular modeling and spectroscopy. And I really missed him. I wish that, inshallah, his good things will be valid and will be stay at the National Research Center, inshallah. To continue our introduction to the conference, actually, in this conference, we have 3 side events. During the conference, it will be a Win2K soft code workshop. This workshop for molecular modeling and the application of a certain program called Win2K in the field of material science. And this workshop will be conducted with one of our professors from Pakistan and with Professor Ihab Abdul Latif and other colleagues from the Atomic Energy Authority. Another side event will be the Science for the Society, Science Cafe. So science, we do believe that science is for the society. Under this theme, Science Cafe will be conducted in this session, some introductory concept for molecular modeling and that interpretation of modeling data will be given. And then how to build a model molecule and how to calculate the infrared spectrum with some interpretation. Then how to assign it with Gaussian program. Moreover, we have some basic principle of molecular spectroscopy, including the FTIR and FT-Raman. And also we will give a little bit some example for how to equip the instrumentation with a kind of a microscope. So the introduction of imaging with both FTIR and Raman will be conducted during this session. The third session will be for sustainable development, and we have some collaboration with Bina Charity. It's a new charity in the Calliope Governorate. With the help of Bina Charity Organization for Sustainable Development, a side event will be conducted to present some introductory concept for sustainable development and how can charity and civil society organization could support this class of important tasks in Egypt. Also, Bina Charity Organization will describe its role in training at Calliope Governorate in Egypt. Based on this consideration, you are welcome to participate in this conference, which gathers scientists from universities and research institutes in order to discuss the recent development in molecular modeling via both national and international scales. The conference has the opportunity to publish the accepted papers in an international journal. And then Professor Amr Abdelghani will be responsible for this special issue, and we will be invited to submit your papers to him, and then it will be refereed by 2 referees. Authors should carefully read over the journal author guidelines in order to put their papers in the required form. We do believe that such kind of events gathering applied and basic science are an important step to integrate both basic and technical scientists to bridge the gap toward building the modern Egypt based on science and technology. We express our appreciation to the contributors for their unreserved cooperation and to the publisher and sponsors for the support. Finally, we are looking forward to your valuable contribution, discussion, and recommendation. Thank you very much.
Thank you, Professor Medhat Ibrahim, for your talk. And now I have the pleasure to invite Professor Aisha Mustafa, the Acting Dean of Physics Research Institute.
بسم الله الرحمن الرحيم. السلام عليكم جميعا. Dear professors and colleagues, you are welcome to the 4th Hybrid International Conference on Molecular Modeling and Spectroscopy, which held at the National Research Center, the largest research institute in Egypt. Molecular modeling is a computer-based technique for drawing and manipulating structures, reaction of molecules, and other properties of compounds that are dependent on 3-dimensional structures. Molecular modeling incorporates various fields such as computational chemistry, drug design, computational biology, nanostructures, and material science. It helps in understanding the fundamentals of physical and chemical interactions, which are difficult to calculate using the experimental procedures. It also helps in the development of new theories, models, processes, and products. Also, the molecular spectroscopy has many applications, such as monitoring diffused oxygen content in fresh water and aquatic ecosystem, determining the atomic structure of samples, determining the metabolic structure of a muscle, studying spectral emission line of distant galaxies, altering the structure of drug to improve their effectiveness, space exploration, characterization of proteins, respiratory gas analysis in hospitals. The aim of this conference is to investigate innovative application and the latest research in the area of molecular modeling and spectroscopy by gathering experienced scientists from universities and academia, as well as institutes, and exchanging their experience with each other and transferring it to the young scientists. The conference program will include 11 keynote lectures from eminent professors in their fields and about 46 oral presentation, in addition to 50 posters in different areas related to spectroscopy and molecular modeling. Besides the workshop, the activity of Science Cafe on the application of molecular modeling in the field of material science. Finally, I would like to thank all guest professors for accepting the invitation and coming to us to provide us with the recent advances in the field of spectroscopy and molecular modeling. Also, I would like to thank the dynamo of the conference, the chairman, Professor Medhat Ibrahim, the co-chairman, Professor Osama Osman, and Professor Hanan Al Hayes, the coordinator, Professor Amr Abdelghani. as well as the organizing committee for their efforts in organizing the conference annually. And I hope all of us enjoy with recent advances in molecular spectroscopy and molecular modeling. Thank you.
Thank you, Professor Aisha, for your speech. And last but not least, I have the pleasure and honor to invite Professor Hussein Darwish, the acting president of the National Research Center, to give his speech.
Bismillah ar-Rahman ar-Rahim, ladies and gentlemen. It gives me great pleasure to welcome all of you in the 4th International Conference on Molecular Modeling and Spectroscopy. National Research Center was established in 1956. It is the largest one relative to all other institutions affiliated to the Ministry of Higher Education and Scientific Research. National Research Center is the largest multidisciplinary R&D center in Egypt devoted to basic and applied research within the major fields of interest. The National Research Center has to correspond to the country's key production and services sectors through the research conducted in different areas of science and technology, as well as scientific consultation and training. I have the pleasure and honor to welcome our guests and participants of the 4th International Hybrid Conference on Molecular Modeling and Spectroscopy. The National Research Center, since its establishment more than half a century ago, is leading the scientific research activities in Egypt in many disciplines, spanning from physics, chemistry, biology, engineering, pharmacology, medicine, agriculture, and earth sciences. Such an interdisciplinary structure provides the fertile foundation for interaction and integration, paving the way for research based on quality and quantity as well. We are pleased to host this conference in the National Research Center, and I am sure the conference will be enjoyable and fruitful for every one of you. I really welcome you again. Thanks.
Thank you, Professor Hussein, for your speech. Ladies and gentlemen, let us now start with the conference first talk.
Thank you to all of you. Now let's start our opening lecture. So I'm going to make an overview for the recent applications of the molecular spectroscopy and the modeling unit at the National Research Center. So the content of this talk will be about the molecular spectroscopy and the modeling unit, and then some research highlights. And I will make a focus on our recent work about the application of microspheres with a focus into two main points. The first one is environmental application. Second one is the use of microsphere in sustained release. And then how to make mass production for these microspheres. Okay, so let's start with the first point. We would like to express who is us. I'm Medhat Ahmed Abdel Khali Ibrahim. I'm the former Dean of Physics Research Institute. I'm working in the field of applied spectroscopy, and this is a bit some of my citation data. I'm lucky to work with a wonderful group in the Spectroscopy Department, also with some institutions in Egypt and outside Egypt. Actually, 6 years ago, we started to make some surfaces through a unit, and this unit called the Molecular Modeling and Spectroscopy Unit. It's headed by Professor Ahmed Abdurrahman Fakhri. He is our symbol. And we part of our group working in the field of material science, and the other working in the field of biophysics. So we are involved in some international events, including Spectroscopy Winter School and the International Conference for Molecular Spectroscopy and Molecular Modeling. And we are in collaboration with some institutions in Egypt. Also, we are involved with a nano club in the rich university in Egypt, and we also have some collaboration with the African Academy of Science. We are involved also with the Academy of Scientific Research and Technology in the Winter School of the application of nuclear sciences in Dubna in the Russian Federation. We have some activities also, not only in basic science, because actually are a physicist, we work in the field of basic science, but we work also in some kind of applied science, and so that we got a golden medal in the exhibition of the Academy of Scientific Research and Technology, and we got a state award in technological science as well. Our winter school last year was ranked among the most important events in Egypt, according to the Ministry of Scientific Research and Higher Education, and it was in collaboration with Nariag in Helwan. Also, we conducted the Science Cafe. We do believe that science is for the society, and in some senses, we do science in casual settings. So we go to some scientists, early career researchers, not only in institution, but outside the institution as well. So we have many scientific events for early career researchers called Science Cafe. Let's go through the research highlights. What we are doing with gathering molecular spectroscopy and molecular modeling. We perform molecular models for investigating electronic properties, structure, and vibration analysis for many systems and molecules. Based on our understanding of the electronic properties, we can consult cost-effective and eco-friendly methods for preparation of nanomaterials and nanocomposites. We can describe the organometallic interaction in the environment and assign a solution based on our understanding of this organometallic interaction. We can design also important nanocomposites, act as a sensor for both gases and biological molecules. So we have some scientific efforts. We have some publication in highly ranked journals, and I'm going to make some spots about what we are doing in the unit. So let's ask a question. How can the materials be smart? If you would like to ask yourself this question, that how can you work with a smart material? So you have to understand first, how can the material be smart? So mimicking biological systems could answer the question. So Allah subhanahu wa ta'ala make everything perfect. So if we are going to mimic a biological molecule, we can understand how can a molecule act like a smart molecule. So let's start with one of the important biological molecules we work with, which is heme molecule. The role of heme molecule is to transport gases, oxygen and carbon dioxide, for example. So it's act like a smart material because it can understand. He got oxygen and then left the oxygen and got carbon dioxide outside and so on. What we can do in modeling with this molecule is to make geometry parameters, infrared and Raman UV NMR, experimentally of course, and make some calculation like total dipole moment, binding energy, mapping molecular electrostatic potential, and calculating the highest occupied molecular orbitals and lowest unoccupied molecular orbitals. Of course, we gather in quantum mechanics together with experimental efforts to understand why this molecule is smart. So let's go through this. Actually, simply, you got oxygen from your nose and then you release carbon dioxide. This means that you have active substrate work to make this transportation, and we do believe that the heme molecule is doing this. We have international collaboration with a colleague from Dubna to understand why this molecule is active. So we make some kind of mapping the electrostatic potential to understand where is the active sites, because you can put the oxygen and calculate this mapping, and then put carbon dioxide and make all of this to understand what is the exact atom responsible for P-smart. To describe this, actually, we gather physics, chemistry, and biology to understand the behavior of this molecule. So let's make this basis together and ask us another question. Could carbon-based materials do the same like biological molecules? So if I got the carbon-based materials, I mean graphene or reduced graphene, graphene oxide, or carbon nanotubes, or fullerene, and so on. Let's try to do this to mimic what happened again. So we make some kind of tuning. I mean by tuning is that we got some functional groups and some metal oxide in nanoscale, and then you have, for example, the first two is the carbon nanotube. If the metal oxide is going to interact with the carbon nanotube, it could be in the surface, could be in the terminal, could be inside, could be in double, and like sandwich-like, could be up and down, and so on. So we ask ourselves, if we put it like this, what will be the physical properties of this molecule, the biological interaction, and so on. Again, with the help of function group, we describe the what happened in the molecules and what happens in the orbitals and the influence of this tuning. We mean tuning that you drive the energy of the molecule, so you can control the chemical, biological behavior of this molecule. By this sense, by this modeling work, we can have a smart material based on carbon nanomaterials. That's why we can make tuning carbon-based material as well as other materials could solve some of the worldwide environmental problems, for example. Let's try to do this. So we have some recent publication. Actually, it was last year, and this we make anti-fouling. We use some kind of core shell material together with natural material in order to make a matrix and build a membrane for the remediation of heavy metals. So you can understand what the molecule can do with heavy metals, how can they interact, and then we ask ourselves, would you like to get this interaction as absorbed state? So you got the metal, and you could remove a metal and use this substrate once more, or you need to make it as a complex. If you are going to use it in a biological system, you can use it as well as like a license, for example. That's why we can describe what's happening in a molecular scale. You can understand what the molecule can do in this interaction, and we got this work also with experimental efforts. We have another one here is to a little bit more complicated membrane. So you are going to use membrane for heavy metals, for cadmium, for example, for lead, and then for arsenic, for other heavy metals to make such kind of interaction. You can understand where is the active site. So mapping the molecular electrostatic potential, and then you could describe what's going on in this scale. So we can go directly in the environment to tune some materials. For example, our colleague Paula Granny is working in some organic pollutants, and then if you can describe what can the photons do in these organic pollutants, you can make some kind of degradation. That's why you have recently some work to enhance the photocatalytic antimicrobial performance of a multifunctional copper-loaded nanocomposite under UV light, theoretical and experimental study. What we can do here that we can degrade. Okay. So we can make a degradation for harmful material by means of nanoscale material with the help of UV. But actually, this work is a little bit expensive. That's why we make another tuning to use the vanadium doped manganese oxide to work in the visible region instead of UV. So by this work, we can a little bit save energy. So molecular modeling could drive the work toward the eco-friendly and cost-effective work. Okay. So let's go directly about the application of microsphere. Actually, we have started 10 years ago to work with Professor Mustafa Suilak to use the water hyacinths in dry form to remediate lead from the aquatic environment. But to use a crude material, it's goes through that the metal could go to the crude material and then it accumulate and go back to the environment. In this sense, we need to make some kind of smart material also. That's why we work with our colleague, Walid Al-Hatabi from Spectroscopy Department, and Dr. Hanan Ibrahim, Dr. Nabila Ammar, also from Water Research Department here at the National Research Center, to produce a microsphere, and this microsphere could act to remediate heavy metals, and we can regenerate metals from this microsphere and use it once more. It was a little bit old work. It's something like 8 years ago. What we do further is to maximize the benefits of the plant and make the plant is cost effective, and we make another microsphere from sodium alginate instead of ketosane. We do this work with Paola Granni in CNR in Italy, and we got some good results. And now we make the solar energy to make heating for the plant, drying the plant instead of electricity. So it's become really cost-effective microspheres, okay? The mechanism is described by us like that. We start that the surface of the sphere is a very huge surface, and we make some kind of complexation on the surface by a so-called functional groups, and also the surface morphology makes some kind of adsorption. So we have two techniques for the removal of metals, but actually we have to test these models through some experimental work like electron microscope, and do this with high resolution electron microscope. We found that the metal is going to accumulate in the surface like this. And we recalculate again our work in order to be quite sure that the water hyacinth microsphere, for example, and sodium alginate and so on could control the level of heavy metals, and will be cost effective and remove the efficiency up to 90%. So we have another application for the microsphere, but in this application is very wonderful that we use a graphene-based material based on our understanding on the behavior of graphene and graphene quantum dots. We make a sodium alginate sphere with graphene quantum dots, and we're going to use it like needle shape. So it's another shape. It's not completely spherical like the old one. For the needle shape, we use it for sustained release. Let me say that what class of release you do it here, we do it with a drug, but we tried later to do it with organic structure. For example, if you are going to use sandy land, like in Egypt, you can put smart fertilizer in the microsphere and make it release it with time. What about the time of release? We can have a look here. Sorry. So the existence of graphene quantum dots make the release rate up to 250 hours. So it extends for more than 10 days. And actually, we put another experiment to do it, the release for organic structure to be for 1 month, for example. So if you got some smart fertilizer, you put it in a sphere and you put it in the desert, it could work for a long time. And we make a comparison between our results and some international results that they release the existence of graphene quantum dots is controlling the sustained release. So we need the microsphere in several applications. It could be used in tissue engineering, in environmental application, in biological application, and so on. That's why we try to use 3D printing technique, the filament type, to make a small and compact device to produce mass production microspheres. That's what we do. We do with 3D printing technology. And then we got this, and we have bought this this compact device as Egyptian patent in the Academy of Scientific Research and Technology. The problem in 3D printing is you have to make a design for your structure. That's why we start with this wonderful design here to put some kind of holes, and if the hydrogel is go through these holes, and it go down to make a microsphere. And we got with this small device 3 kilograms of microsphere in 1 hour, which is a very big number. And we can also have another device to make 10 kilometers in 1 hour. So you can bump the hydrogel toward this small device, and it will be something like this, okay? And we can use it like this in the laboratory. And this is our recent advances in the production of microspheres, okay? So conclusion and outlook, I would say that we are willing for collaboration. We are not only in the National Research Center, but our colleagues from Ain Shams University, Cairo University, from Argis University in Turkey, and CNR Rome, and also some colleagues in Dobna, and we are willing for collaboration with all of you, if possible, of course, okay? So if someone would like to ask me, I think we have a couple of minutes for questions. Was it clear enough? Alhamdulillah. group photo before we start the practice lecture. So now Rania Badri is going to present the development of carboxyl cellulose sodium carbon oxide nanocomposite with structure and UV blocking properties. Please, you have 10 minutes.
Hello everybody, I'm Rania Badri, Assistant Lecturer at Physics Department, Faculty of Women, Ain Shams University. First of all, I would like to thank Professor Medhat Ibrahim for giving me this chance to contribute in the first international conference on molecular modeling and spectroscopy. Our talk today will be about the development of carboxymethyl cellulose sodium copper oxide nanocomposite films with structural and UV blocking properties. This work under supervision of Professor Nadra Nada, Professor Mahmoud Muhammad Al-Nahas, Professor Hanan Al-Hayes. Let's start with our contents, introduction, aim of the work, preparation methods, characterization techniques, results and discussion, and conclusion. Introduction. As we know that the UV radiation is a part of the natural energy produced by the sun, and it has a shorter wavelengths than UV visible. So your eyes can see UV radiation, but your skin can feel it. Recently, there is a progressive increase in the UV radiation reaches our atmosphere, and this radiations have a harmful effects on human health. And this is due to the depletion of the stratospheric ozone layer. The generated UV rays are divided into 3 regions, UVA, UVB, and UVC. The progressive increase in the number in the UV radiations promotes a number of harmful effects on human health, such as, skin poorness, skin cancer, hyperpigmentation, and cataracts. The penetration of UV radiation to the layers of the skin. In the case of UV rays, UVB rays can penetrate and damage the outermost layer of the skin, and overexposure to UV rays causes sun poorness. However, UVA rays are capable of penetrating the outermost layer of the skin, and it contributes to the development of skin cancer, as it can penetrate our skin more deeply. Most of the UVC rays are absorbed by the oxygen molecules presented in our atmosphere. However, in using sunscreens, all of the incident UV rays are reflects. Biopolymeric materials such as cellulose, chitosan, and starch may or may not be capable of absorbing UV radiation, and this is due to the structural chemical composition of the polymers. Thus, in order to increase the absorption of UVB, nanomaterials having an absorption band are added. As we see that in this figure, that adding nanomaterials with small concentration results in an increase in the absorbance in the region of UVC. However, increasing the concentration of nanomaterials results in an increase in the absorption until it extends to the 3 regions of the UV radiation. As an example of biopolymers is carboxymethyl cellulose sodium, which is abbreviated as CMC, is one of the cellulose derivatives, and it is a polysaccharide polymer, has a number of advantages like non-toxic, inexpensive, and water soluble, and this is the molecular structure present as CMC. CMC can be used as a thickener, stabilizer, carrier, emulsion in the field of food industry, textiles, papers, pharmaceuticals, and cosmetics. The aim of this work is to develop a new polymer nanocomposite filters based on CMC and copper oxide nanoparticles for the efficient block of UV light. Preparation methods. Copper oxide nanoparticles are prepared utilizing the precipitation method as presented in this scheme. However, the nanocomposite samples are prepared utilizing the casting method according to this table. Characterization techniques. The prepared nanocomposites are characterized utilizing XRD, FTIR, and UV visible spectrophotometer. Results and discussion. This figure presents the XRD pattern of copper oxide nanoparticles. The sharp peaks indicates the good crystallinity of the prepared copper oxide nanoparticles and the absence of any secondary phases confirming the purity of the prepared nanoparticles. Also, the obtained pattern is well indexed to the monoclinic structure of copper oxide, which is the sternite structure, and we use this equation for the monoclinic unit cell to determine the lattice parameters, which are in good agreement with that of the reference CARDIS. Also, we calculated the average crystallite size of copper oxide nanoparticles using Shearer equation, which is 3.6 nanometer. This figure presents the XRD pattern of CMC copper oxide nanocomposites, and it's clear that there's a broad peak at nearly 2 theta equal 20 degree, which is due to the amorphous nature of CMC. Increasing the concentration of copper oxide reduces the peak of this peak, the intensity of this peak, and also there is a remarkable peaks of copper oxide appeared with increasing the concentration of copper oxide. This confirms the good formation of the nanocomposites. We calculated also the crystallite size, microstrain, dislocation density, and the number of crystallities for the prepared nanocomposites, and we found that the crystallite size decreases with increasing copper oxide concentrations. This figure presents the FTIR absorption spectra of copper oxide, which contains only 3 absorption bands, which are assigned to the copper oxide stretching vibrations, and the absence of any secondary phases are ruling out the possibility of appearance of another peaks. This figure presents the FTIR absorption spectra of CMC and CMC doped with different concentrations of copper oxide. The characteristic bands of CMC are observed with decreasing intensity. However, a high intensity peaks assigned to copper oxide nanoparticles are also observed. This confirms the good interaction between CMC and copper oxide. This table presents the FTIR band assignment of CMC and CMC copper oxide nanocomposites. We observed that the characteristic bands of CMC undergoes a strong shift with the addition of copper oxide, and this confirms that a strong interaction has been occurred between CMC and copper oxide and the formation of hydrogen bonding between these 2 materials through this absorption bands. UV visible spectrophotometer. This figure presents the FTIR absorption spectra of CMC and CMC doped with different concentrations of copper oxide. There are 2 absorption bands are observed. The first absorption band is due to the pi-pi star transition of CMC. However, the second absorption band, which is redshifted with increasing copper oxide concentration, is due to the copper oxide nanoparticles. We calculated the absorption coefficient using this equation, and we found that by extrapolating the straight line of the portions of all curves, we obtain the fundamental age of absorption for all samples. And the presence of 2 absorption shoulders indicates that there are 2 values of the optical band gap. Also, this shift confirms the decrease in the optical band gap. We calculated the type of transition of, in CMC by making the first derivative to the Toke equation, and we found that it is an indirect allowed transition. We determined the optical band gap utilizing 2 models, Toke model and absorption spectra fitting model. The 2 models are consistent with each other, that the band gap energy decreased with increasing copper oxide concentration in these 2 models, and also the 2 models confirms the presence of 2 values of the optical band gap with the addition of copper oxide, and this is due to the creation of the localized states within the forbidden band gap of CMC. We calculated the Auerbach energy using this equation in order to determine the width of the localized states. Okay. We calculated the transmittance spectra. This figure shows the transmittance spectra of CMC and CMC doped with different concentrations of copper oxide, and we observed that the transmittance decreases with increasing copper oxide concentration until it reaches to its minimum value, nearly 1.1% for CMC containing 8% of copper oxide. We calculated the opacity of CMC using this equation. There is a problem in the show of these slides. I don't know what is the reason. Also, a simple visualization was determined for the CMC and the nanocomposite samples. CMC, which are their colors gradually changes from transparent to relatively dark and to relatively dark color. Conclusion. The prepared nanocomposites based on CMC and copper oxide nanoparticles were successfully prepared utilizing casting method. XRD confirms the formation of the nanocomposites. FTIR results confirming the formation of the hydrogen bonding between CMC and copper oxide, and also the decrease in the optical band gap and the decrease in the transmittance value confirms the creation of the localized states between the HOMO and LOMO band gap of the CMC. And this tunable optical characteristics confirms that the prepared nanocomposites can be utilized as a UV blocking materials and various optoelectronic devices. Thank you.
Thank you very much, Rania Badri. Actually, at the end of the session will be around table discussion, okay? So the discussion will be postponed to the end of the talks. And now the talk is for our colleague from Algeria, Ahlam bin Khalifa. She's going to make a presentation about investigating thermal behavior of polymer networks based acrylic monomers through atomistic molecular dynamics simulations. So please.
Hello everyone and welcome to my presentation. First of all, let me thank you all for coming here today. Then I'd like to thank the organizers of this meeting for accepting me in this conference. My name is Bint Khalifa Ahlam and I'm a PhD student at the University of Tlemcen, Algeria. I work in the field of materials characterization and composites, and my research focuses on shape memory polymers and dynamic molecular simulation. So as you can see on the screen, our topic today is about theoretical and experimental investigation of the thermal properties of cross-linked copolymer based on acrylic monomers. This presentation is structured as follows. First of all, I'd like to give you an overview of shape memory polymers and their applications. Next, I'll focus on materials and methods of characterization. Then I'll go to highlight what I see as the main points of our results in discussion. And finally, I will present the conclusion of our contribution. So in the last years, the shape memory polymers have attracted much attention from researchers due to their good mechanical properties and similar spans. What is a shape memory polymers? Shape memory polymers are a new kind of active and deformable materials which have the capacity to change and recover their initial shapes in response to an external stimulus, such as a temperature, light, magnetism, electricity. Shape memory polymers are an exciting area of polymer innovation. The range of application of such material is huge, covering medical, electronics, textile, and others. And the development across all of this area is still ongoing in laboratories around the world. Generally, thermally activated shape memory polymers are the most reported shape memory materials. This last can be characterized by a thermomechanical cycle, which consists of 3 steps. The first step is the shape programming, in which the sample is heated to deforming temperature above the glass transition temperature Tg in order to become flexible and easy to deform. Then the material is deformed to other shapes and cooled below Tg to fix the temporary form. And finally, in the recovery step, the sample recovers its permanent shape when it is heated above Tg. Actually, with the increasing demand for development of new smart materials in different applications, photocrosslink acrylate shape memory polymers have become excellent and promising candidates. This is why in our work, a series of shape memory polymers based on HPMA, hydroxypropyl methacrylate, and isobonyl acrylate were prepared with the same crosslinker concentration and UV irradiation. HPMA is a good useful hydrophilic monomer for various applications, especially in biomedical application. It has an excellent biocompatibility and non-toxicity. Then the analysis was performed using infrared spectroscopy. The spectra of both samples show the acrylic double bond CC, especially in the band of 810 and 1636. This two absorption band can be used to describe the polymerization process and evaluate the conversion of acrylic double bond in the resulting networks. As you can see, all the samples show the same decreases in the concerned absorption band. A very small intensity is observed after 45 minutes, corresponding to the negligible amount of unreacted monomers. However, the evolution of the conversion rate of acrylic also confirms that all the systems show a very fast polymerization rate after 10 minutes of polymerization and start to saturate after 20 minutes. Finally, the highest conversion value between 89 and 98% means the total polymerization of all the acrylic monomers existing in the systems. In the simulation part, the KDJ software is used for the generation of the different systems, for the energy minimization, equilibrating system, and calculating the energy functional forms with the Drayden force files. The different macroscopic and the shape memory properties were done by the LAMP software, and finally the results obtained from the latter are visualized and interpreted by the VMD software. Then to predict the glass transition temperature of polymer system in molecular dynamic simulation, we often use the theoretical approach called diatomic method. It consists in following the change in the density of the system as a function of the temperature variation. By plotting the values of inverse of the density or specific volume for each temperature, and it is possible to define an estimate of GG value. With the molecular dynamic simulation results, it is verified that the amount of isobornyl acrylate has a significant impact in the shape memory performance, including shape recovery and shape fixity. The system shows a good recovery performance of around 88% when the isobornyl acrylate increases to a certain value, while the HPMA improves the shape fixity of the systems. Finally, it can be concluded that shape memory polymer containing a higher concentration of isobornyl shows the best ability to recover its permanent shape in the recovery step. However, the shape fixity property is quite low compared with the SMP containing a big amount of HPMA. You can find more information on my current research project on my research paper, Enhancement of Shape Memory Properties of Thermoresponsive Copolymer based on HPMA and isobornyl acrylate. And you can also reach me via email. I'm always happy to connect, share information, and discuss. And thank you for your attention. Hello everyone, and welcome to my presentation. First of all, let me thank you all for coming here today. Then I'd like to thank the organ.
I'm sorry for this technical problem. I'm really sorry. So the next speaker will be Dr. Ahmed Refat from Sesame, Jordan. He's going to present the recent advances in sensors. So please.
First, let me thank you for being here today. My name is Ahmed Refat, Associate Professor of Applied Spectroscopy, and my presentation is titled Recent Advances in Sensors. Let me start with a brief introduction. Sensors are devices that can detect, quantify, and respond to an input stimulus from the physical environment. This response is either directly or by converting this input stimulus to a signal for processing by other special systems. The output signals are normally functionally related to the input stimuli, and sensors can quantify almost everything of physical, chemical, or biological concern. So the input stimulus can be light, humidity, heat, motion, chemical reaction, or any other phenomenon. This interesting historical timeline of sensor development technology describing that sensor technology started as early as 105 AD, and the progress has been going on since then. If we talk about the classification of sensors, I must say that there are different ways that can be used to classify or categorize sensors. The first one is based on their mode of operation, in which they can be classified into passive sensors or active sensors. Passive sensors, as you can see in this photo, they can detect and respond to some type of input from the physical environment, while the active sensor requires an external source of power to operate. If the sensors are classified based on the input-output signal conversion mechanism, they can be classified into number one, thermoelectric sensors. And these sensors produce electrical signal in response to change in temperature, and so they have wide application in medicine. Second one is electrochemical sensors. They produce electrical signal in response to a predefined chemical interaction, as we will see in some of the examples I'll show you later. And as you can see in this photo, the thermite is prepared for a predefined chemical interaction, and when it happens, the signal is produced. Thermo-optic sensors, they generate signal in response to change in temperature or refractive index, and they are most commonly used, for example, in motion sensors, and in these new light bulbs that are switched on automatically when they detect a motion in its field. And the last one is electromagnetic sensors. They generate signal in response to change in conductivity or permittivity, and so they are also subcategorized into inductive time and capacitive time. The inductive time, they detect metallic objects causing disruption in the electromagnetic field produced by the sensor, while the capacitive time detect non-metallic objects having a dielectric constant different from that of air. Before proceeding to the broader and more detailed way of classification of the sensors, it is important to mention that the major and most important part of sensors study is the one addressing its performance. And so specific parameters must be studied in order to assess the performance of a sensor. And these parameters include sensitivity, which is the measure of the change in the output signal of the sensor relative to the unit change in the input stimulus. The second one, and actually one of the most important parameters, is the resolution, which is the smallest amount of a change in the input that can be detected and accurately indicated by the sensor. The third one is linearity, which is the detection range that can be graphically represented as a straight line, which is often determined by the calibration curve. Response time and recovery time. Response time is the time the sensor takes to react to a given input stimulus, and it's easy to assume that as the response time is shorter, the better the performance of the sensor. And then the recovery time, which is the time for the sensor to return to the baseline value after the step removal of the measured variable. And also, the shorter the recovery time, the better the performance of the sensor. And finally, repeatability and reproducibility, they both can be representing the same parameter, except that repeatability is the deviation between measurement in a sequence when the object under test is the same, while reproducibility although the same as repeatability, except that it also incorporates long time intervals between subsequent measurements. As I said, the more broader and more detailed way of classification of the sensors is classifying them based on their applications. The first one is the gas sensors. They are designed for and are capable of detecting the presence of many dangerous gases, such as those of toxic or explosive nature, in addition to volatile organic compounds, and are also able to quantify them. And gas sensors are actually very important because they are detecting things that we cannot see with our eyes. And sometimes some gases are odorless, and so here comes the importance of gas sensors. They are commonly designed using metal oxides and the carbon nanomaterials, in addition to thin polymer films and electrochemical solid-state galvanic sensors. Let us start with this first example. This paper is titled Enhancement of the Sensitivity and Selectivity of Alpha Ferrous Oxide Nanorod Gas Sensors by Zinc Oxide Nanoparticles Decoration. Here, alpha ferrous oxide nanorods were decorated using zinc oxide nanoparticles, which significantly enhanced the sensing properties towards hydrogen sulfide in terms of faster sensor response and higher intensity sensing response compared to pure alpha ferrous oxide nanorods. As with other nanoparticles, this enhancement is attributed to the increased sensing surface area, which took advantage of the very, very small particle size of the nanoparticles and the formation of more than one depletion zone on the surface of the nanocomposite, leading to decreased resistivity. The best performance achieved was for 300 ppm of hydrogen sulfide at 300 degrees Celsius, with a response time of 164 seconds and recovery time of 173 seconds. As a common trend with the progress in sensor technology, the progress in the production of sensors includes either the introduction of novel materials or preparation methods for the fabrication of sensors, or enhancement of the performance of the already available materials or compounds commonly used in sensor development. As we can see here, some other examples for gas sensors based on different materials or with enhanced properties. And here are also other examples. And this is the general trend with different types of sensors, including biosensors, gas sensors, smoke sensors, and so on. Here is another interesting example of a gas sensors I would like to show you. In this study titled Nano Architecture of Highly Sensitive Tin Oxide-Based Gas Sensors for Acetone and Ammonia Using Molecular Imprinting Technique. The authors of this study used the molecular imprinting technique by preparing a specific mold on the substrate used at the sensor substrate. They used acetone template and ammonia templates, and so the sensor is ready to detect those two specific gases. This sensor showed very good performance. As a result, demonstrated high sensitivity of about 90% for ammonia, and the detection limit was as low as 600 parts per billion. While for acetone, the sensor device demonstrated high sensitivity of about 77% with a detection limit of 280 parts per billion. The second type of sensors are called temperature sensors. They are currently applied in various fields, including industry, agriculture, and healthcare, in addition to their long-known common applications in the control of different devices such as air conditioners and refrigerators and freezers. Let me start with this first example. It's called, the paper is titled Organic Temperature Sensors Based on Conductive Polymers Patterned by Selective Wetting Method. This study on the temperature dependence of the electrical conductivity of conductive polymers. Organic temperature sensors based on polymer 3,4 ethylene dioxythiophene as a conductive polymer was constructed as a temperature sensor. The technology used here is called inkjet printing, and the sensor was fabricated in the form of patterned resistors of PEDOT-based polymer. These resistors demonstrated minus 0.75% per degree Celsius. Temperature coefficient resistant at 23 degrees Celsius, and the temperature coefficient resistant as shown down here, it is the calculation of the relative change of resistance per degree of temperature change. These sensors show a very small variation of resistance coefficient of about 4.1%. The results in this method were comparable to those obtained by metal resistors. These metal resistors were used in this study as references to compare the performance. Results suggested that the fabricated sensors here in this study could operate at a low temperature range from minus 10 degrees Celsius up to 80 degrees under normal conditions. And here are other examples of temperature sensors based on different materials or different preparation methods, such as silver nanowires or photonics or fiber optics, and also inkjet printing techniques. The third type are humidity sensors, and these are used to detect and quantify water vapor and represent what is known as relative humidity. They are widely applied in controlling heating, ventilation, and air conditioning systems, and so they serve in different applications, which include preserving pharmaceuticals and controlling preservation conditions in museums, greenhouses, meteorological stations, and hospitals. This example from a paper titled "High Performance of Calorimetric Humidity Sensors Based on Minerals." In this study, the authors used bromothymol blue as an indicator for humidity, titanium dioxide, perovskite, and molybdenite were chosen as the host of the calorimetric humidity sensor. There was a notable response by BTB, titanium dioxide, that was observed to the RH of 11, 23, and 75% at 1 minute at 25 degrees Celsius. The BTB perovskite demonstrated a better response, especially at lower values of relative humidity around 11%. Results indicated that the performance of the sensor was clearly affected by the surface area, and so the capability of BTB and water absorption would significantly enhance their performance. And you can see here the change in color, the color of bromothymol blue in response to change in the value of relative humidity. These are other examples of humidity sensors based on gold electrodes, based on laser-induced graphene porous electrodes, and or carbon-based flexible humidity sensors using cellulose nanofibers. The fourth category of sensors is represented by smoke sensors. And when talking about smoke, we are essentially talking about air pollution. And so air pollutants represent a class of the most hazardous pollutants to human beings and animals owing to the toxic effect they pose on skin and eyes, as well as other living tissues, especially, as I said, those exposed, normally exposed to air pollutants. And over the past decades, special attention has been given to maintaining the adequate quality of urban air, because air pollution, as we all know, has reached dangerous levels to human health. The most common causes of air pollution are unburned gases such as carbon monoxide and nitrogen oxides and sulfur oxides, which are considered the major sources of air pollution. And the main sources of these gases include industries, vehicles, aircrafts, fumes, and the petrochemical plants. In this study, a sensor sensor for fire smoke detection. In this study, the authors wanted to introduce a new false fire alarms that might be activated by non-fire aerosols. So they developed a novel outer mean diameter sensor that is based on dual wavelength, 450 nanometer blue light and 950 nanometer infrared light instead of smoke concentration for fire detection. I just must clarify, outer mean diameter is the average of particle size, is defined as the diameter of a sphere that has the same volume surface area ratio of a particle of interest. An extra correction has been introduced by the authors of this study by adding an extra correction channel that has been added to the fabricated sensor in order to quantify aerosol samples with varying particle size and different refractive indices while maintaining a low error of measurement. And so it was inserted as a reference in order to separate between real fire alarms and false fire alarms. Results of this study confirmed the ability of the sensor to promptly activate the alarm to fire smokes while avoiding false fire alarms caused by non-fire aerosols. Another 3 examples of smoke sensors, as you can see, against smoke sensors based on breach 58 functional line, residual oxide nanostructures, and another one based on flexible and porous graphene composites, and the third one, highly sensitive and selective room temperature smoke and humidity sensor based on chemically grown porous hydrangea type bismuth molybdate. The last category of sensors in this classification are biosensors, which are devices that contain a specific receptor molecule ready to detect and to respond to a specific measurement, and a physicochemical transducer is used to generate the measurable signal relative to the input stimulus. Biosensors date back to 1962 when the first blood-brain screening biosensor was developed in order to monitor blood gases during surgeries. Nowadays, the most frequently used forms of biosensors which are very simple, like home pregnancy tests and glucose detectors, with strong modification, increasing every day to introduce new classes of sensors for wide range of application, including nucleic acid tests, food analysis, and drug detection.
I think we are exceeding in time. Let's prepare for the next speaker.
Essentially help in the introduction of novel, advanced, robust, accurate, and fast responsive system, having the ability to detect the changes in the levels of the specific measurement under study or that's required to be detected, associated with the presence of a certain disease, and so they can provide faster diagnosis and consequently faster treatment of many diseases. This paper is titled "The Biosensor Component of Integrated Glucose Oxidase with Nitrogen Microreactors."
Thank you, Dr. Ahmed Rifat. Thank you very much.
And so it has a potential application and monitoring of.
But according to the time schedule, we have to move to the next speaker. Okay. The next speaker will be Dr. Hind Izzat from Nano Unit Solar and Space Research Department, National Research Institute of Astronomy and Geophysics, Helwan, Egypt. The talk will be about studying the optical and thermal properties of ketosene zinc oxide and the ketosene zinc oxide graphene oxide hybrid nanocomposite. Please, you have 10 minutes.
Hello, everyone. It's a pleasure to be here with you at this important conference. Let's start with outlines divided into introduction, aim of the work, sample preparation, result and discussion, and finally the conclusion. As known, nanotechnology is defined as the design, fabrication, and utilization of structured materials and devices by controlling shape and size less than 100 nanometer. The significance of this technology is determined by its use in a variety of fields, including the environment, agriculture, biotechnology, electronics, energy, medicine, and aerospace. According to my specialization in space application, we focused on nanotechnology for aerospace material. Such materials for space should have unique properties to suit the space environment, such as low weight, high resistant to extreme condition, and high strength. Such as materials are used for various applications, including sensor, optoelectronic material, coating, UV, sensing, X-ray shielding, and so on. Nanomaterial are classified as organic, such as carbon-based material, which have significant properties such as functionality, along with enhanced mechanical, electrical, and thermal stability. Inorganic materials, such as metal oxides, have important properties such as functionality, along surface area, and narrow band gap. In addition to improving optical, electrical, and sensing properties, also the third classification is hybrid composite. Hybrid composite are made up of two or more organic or inorganic components, at least one of them in nanoscale. There are different types of nanocomposite, polymer-based and non-polymer-based. Polymer-based nanocomposite could solve many of weight and process-based problems, plugging the space industry, and offer new capability for future systems. Natural polymers are preferred recently according to the use of green technology, which is defined as the sensing or hybridization of nanomaterial with natural bioactive compounds. This is a low-cost, eco-friendly, easy to manage, and non-toxic technology. So the aim of our work is to use green nanotechnology to prepare hybrid composite, hybrid nanocomposite with a simple, eco-friendly, and low-cost technique. Study the impacts of nanofillers on the physical, chemical, and thermal stability of new composite. Study the optical and thermal properties of the product composite. So to achieve our aim, we prepared our samples as follow. The precipitation method was used to prepare zinc oxide for nanomaterial with zinc acetate as a metal salt and sodium hydroxide as a precursor. Also, graphene oxide was prepared using Hammer's method, using a mixture of sulfuric acid and potassium permanganate. Then ketosene zinc oxide nanocomposite were prepared with zinc oxide different concentration from 10% to 15% of the weight using the casting method by ketosene soluble in distilled water with acetic acid, then adding zinc oxide to the solution before casting. Ketosene zinc oxide, graphene oxide nanocomposite were prepared using two different methods, casting method and as mentioned previously, and the one-pot method. One-pot method was used by combining soluble ketosene, soluble zinc acetate, and soluble graphene oxide, then adding sodium hydroxide drop by drop to achieve the pH of 10. The one-pot all samples were conducted using very high-tech techniques that show the result of hybridization. We started by characterizing prepared nanomaterial. For zinc oxide, FTIR showed the two-band characterized the formation of zinc oxide at the nanoscale. Also, UV spectra of zinc oxide nanoparticle will observe it at a peak at 376 nanometer. For prepared zinc oxide, also conducted by scanning and transmitting electron microscope, showed that the particles are mostly spherical in shape and aggregate into a large particle morphology with particle size ranged from 20 to 59 nanometer. For graphene oxide, the FTIR showed the characteristic bands of graphene oxide nanosheet. The absorption band were specified for the carboxyl carboxyl group stretching and the CC of graphene sheet in 1713 and 1575 centimeter minus 1 respectively. In addition, absorption band appeared at 4,021 centimeter minus 1 and was attributed to the OH function group. COC stretching and the CO vibration also be due to the carboxylic acid and carbonyl groups located at the edge of graphene oxide in the two absorption band around 1,280 centimeter minus 1 and 1,049 centimeter minus 1. The UV spectra of graphene oxide relative a maximum absorption peak at 2029 nanometer due to the pi star atomic CC bond transition and a shoulder absorption peak at 341 nanometer due to the N pi star aromatic CO bond transition. Graphene oxide image, the surface appeared randomly aggregates as similar thin sheets with separate edges, wrinkled surface and folding. For ketosane zinc oxide nanocomposite, the FTIR results show the characteristic spectra of ketosane with a presence of zinc oxide affected on the ketosane spectrum by shifting bands to the higher wave number, which confirmed the interaction between zinc oxide and the ketosane through the NH2 group, which make a change in molecular structure from acetyl to deacetyl ketosane. Ketosane and zinc oxide were also characterized using proton NMR. The main characteristic beats of ketosane proton were shown as follow. For ketosane zinc oxide, all the peak related to completely deacetyl ketosane appeared with the disappearing of the NH and the CH3. Furthermore, proton from NH2 vanished, including the zinc oxide and the ketosane are coordinate via it. The broadness of the peak in the is an indication of metal appearance according to the paramagnetism, which confirmed the coordination of zinc oxide with ketosane through NH2 group as indicated in FTIR spectra. Also, scanning result of ketosane zinc oxide. Scanning result showing ketosane surface have a small pores that are distributed uniformly on the composite surface. With the addition of zinc oxide, the pore size increased, and with increasing the filler, the pore became less porous, with the appearance of white spots referring to zinc oxide agglomerated on the ketosane surface. For the FTIR spectra of hybrid composite with the two different preparation methods showing the typical ketosane band of the two samples, a new band appeared at 1657 and 1652 centimeter minus 1, which is assigned to the carboxyl group from graphene oxide and is downshifted because of hydrogen bonding between the graphene oxide and zinc oxide. There is a shift in the NH2 group to higher wave number at 1549 and 1560 centimeter minus 1. This shift reflects the interaction between ketosane and zinc oxide through NH2. Then a relative band around 472 and 474 centimeter minus 1, which was attributed to the carboxylic function group formed by the interaction of zinc oxide oxygen carbon. Relocated the characteristic zinc oxide stretching vibration frequency to a higher wave number. Scanning image of ketosane zinc oxide graphene oxide prepared by casting revealed the white spots that were distributed along the sample surface and accumulate in some area. However, for the one-put sample, there is a small white rod shape and other agglomerate on the ketosane surface, which indicates that there are many interaction between the ketosane zinc oxide and the graphene oxide edges. The UV spectra of ketosane zinc oxide and composite of ketosane zinc oxide graphene oxide showed a maximum absorption band at 206 nanometer for ketosane. There is a shift in the peak of ketosane toward the longer wave number. The move toward the longer wave number suggested that the doped sample will have small band gap. The presence of delocalization along the polymer chain has been stated to be due to the strong changes toward the longer wave number. And there is a weak band at 315 nanometer that increases with increasing the filler, which indicated the miscibility and the interaction between ketosane and both zinc oxide and the graphene oxide. In the one-put hybrid, there is an absorption peak at 252 nanometer attributed according to the interaction between ketosane and graphene oxide, zinc oxide. Also, the absorption coefficient The absorption coefficient is determined by the following relationship. The value of the absorption age decreased compared with the pure ketosene, and the lowest value was for the one-boot composite. According to our correlation between ln alpha and HNU, ketosene doped with both zinc oxide and graphene oxide give higher value of band tail energy compared to the other samples, which means that one-boot composite has a higher degree of disorder and has highly conductivity. Values of both direct and indirect band gap are calculated also, as seen with increasing the filler. The value of direct and indirect band gap energy decreased compared to pure ketosene, and it was a lower value for ketosene doped with zinc oxide and graphene oxide. Previous results showed that the ketosene zinc oxide graphene oxide prepared using one-boot hybrid method reduced the order and is the best preparation method for the use of ketosene zinc oxide graphene oxide as optoelectronic material. Also, thermal gravimetric analysis were conducted to study the thermal behavior of prepared sample. This result showed that ketosene zinc oxide nanocomposite and ketosene hybrid composite had higher residual mass percentage relative to the presence of zinc oxide and graphene oxide due to the rise in temperature. In addition, a certain improvement in the degradation behavior of composite relative to ketosene changed from 22 to 79 percentage, which could decrease the degradation of ketosene with increasing the filler. And the highest percentage was for one-boot nanocomposite. So the ketosene zinc oxide nanocomposite exhibit a significant enhancement in thermal stability compared to pure ketosene. Also, the hybrid composite one-boot material exhibit more thermal stability than all other samples. Finally, we can conclude that our work as the ketosene zinc oxide graphene oxide hybrid nanocomposite was prepared with different method of casting and one-boot, verifying using FTIR and NMR spectroscopy, which confirmed that the interaction occurs through the NH2 function group of ketosene and the zinc oxide, and the carboxyl group of graphene oxide. The electronic and optical properties of nanocomposite are affected differently by the shape and the particle size of zinc oxide. The one-boot hybrid method has most enhanced properties, which confirms the theoretical model. In addition, preparing ketosene zinc oxide graphene oxide can be used as optoelectronic material. Finally, I would like to thank you all for your attention, and I am waiting for discussion.
Thanks a lot, Dr. Hendazda, for your nice presentation. And now,
hello everyone, I'm Rania Badri, Assistant Lecturer at Physics Department, Faculty of Women, Ain Shams University. First of all, I would like to thank Professor Medhat Ibrahim for giving me this chance to participate in the first international conference on molecular modeling and spectroscopy. Our talk today will be about structural and UV blocking properties of carboxyl cellulose sodium copper oxide nanocomposite films. This work under supervision of Professor Nadra Nadra, Professor Mahmoud Al-Nahas, Professor Hanan El-Hayes. Let's start with our contents: introduction, aim of the work, preparation method, characterization techniques, results and discussion, and conclusion. Introduction. As we know that UV radiation is a part of the natural energy produced by the sun and has shorter wavelengths than visible light. So your eyes can't see UV radiation, but your skin can feel it. Recently, there has been a progressive increase in the UV radiation due to the depletion of the stratospheric ozone layer. The generated UV rays are divided into three regions based on the wavelength of the incident radiation, called UVA, UVB, and UVC. The progressive increase in the UV radiation promotes an increase in the number of harmful effects on human health, such as skin poorness, skin cancer, hyperpigmentation, cataracts. And this is because when UVB rays incident on our skin, it penetrates and damages the outermost layer of our skin, and overexposure to UVB causes sun poorness. However, UVA rays cause tanning and contribute to the development of skin cancer, as it can penetrate our skin more deeply. However, most of the UVC rays are absorbed by the oxygen molecules presented in our atmosphere. However, when using sunscreen, all of the incident UV radiations are reflects. Biopolymeric materials like ketosene, cellulose, starch are derived from natural sources with good biocompatibility and good biodegradability. The present biopolymer materials may or may not capable of absorbing UV radiation, which also depends on the intrinsic components of the polymers. And this is due to the lack of the pi-pi transition, and hence absorption is difficult or very weak in the UV region. Thus, present biopolymeric materials may allow all UV, visible, and near IR radiation to pass during exposure. However, to enhance the UV protection and blocking of this biopolymeric films, nanomaterials having absorption band in the UV region are added. And as we see in this figure, that present biopolymeric materials may transmit all of the incident UV radiation. However, adding nanomaterials with small concentrations may increase the absorption of UV radiation in the UVC region. Increasing the concentration of nanoparticles, it also increases the absorption of the UV radiation to be in the regions of UVC and UVB. However, increasing the concentration of nanomaterials, it could be extend the absorption of UV radiation to be included in the regions of UVA, UVB, and UVC. As an example of biopolymers is carboxymethyl cellulose sodium, which is one of the cellulose derivatives, and it is a natural polysaccharide polymer present in nature with abundance and non-toxic, inexpensive, and water soluble. And this is the molecular structure presented CMC. CMC has a number of applications as a thickener, stabilizer, carrier, emulsion in the industry of food, textiles, papers, pharmaceuticals, and cosmetics. Aim of the work. The aim of this study is to develop a new polymer nanocomposite filters based on CMC and copper oxide nanoparticles for the efficient block of UV light. Preparation method. Copper oxide nanoparticles were prepared using the precipitation method by following the steps presented in this figure. However, nanocomposite films based on CMC and copper oxide nanoparticles was prepared utilizing casting method as presented in the following scheme, and this film presents the final form of the CMC copper oxide nanocomposite sample. Characterization techniques. The produced nanocomposites will be characterized utilizing XRD, high resolution TEM, FTIR, and UV visible spectrophotometer. Results and discussion. This figure presents the XRD pattern of copper oxide nanoparticles that was collected in the region of 2 theta equal 25 to 80 degree. The sharp peaks observed confirm the good crystallinity of the prepared copper oxide nanoparticles. The obtained XRD pattern of copper oxide is well indexed to the monoclinic structure of copper oxide, tenorite structure, and the absence of any secondary phases indicates the presence of only copper oxide nanoparticles and the high quality of the nanoparticles synthesized. Using this equation for monoclinic unit cell, we calculated the lattice parameters of the prepared copper oxide nanoparticles, which is with good agreement with that of the card. This table presents the calculated crystallite size, dislocation density, microstrain, and the number of crystallites for the most prominent peak of copper oxide nanoparticles, which was calculated using the following equations. This figure presents the XRD pattern of CMC and CMC doped with different concentrations of copper oxide nanoparticles. It can be seen from the figure that CMC and CMC nanocomposite films have a broad peak near to theta equal 20 degree due to the amorphous nature of the CMC. It could also be deduced that the intensity of this peak decreases with increasing copper oxide nanoparticles, and it can be as a result of the crystallite size reduction and microstrain generation. The addition of copper oxide nanoparticles as a nanofiller to a pristine CMC film was confirmed by the presence of a number of remarkable peaks of copper oxide nanoparticles and a decrease in the intensity of CMC peak and an increase in the copper oxide peaks with increasing the copper oxide concentration. Additionally, crystallite size, microstrain dislocation density, and the number of crystallites were calculated for the most prominent peak in the nanocomposite films. The decreasing the crystallite size confirms the decrease in the optical band gap of the prepared nanocomposite. The high resolution term of the copper oxide nanoparticles confirms the aggregation of the copper oxide crystals and the formation of clusters with crystallite size higher than that obtained by the XRD. However, the selected area diffraction pattern confirmed the presence of copper oxide nanoparticles and the lack of any other phases of copper oxide. This figure presents the FTIR absorption spectra of copper oxide nanoparticles, which contains only 3 absorption bands that can be attributed to the copper oxide stretching vibration. Additionally, no other IR active mode was seen in this region, ruling out the possibility of another phase. However, this figure presents the FTIR spectra of pure CMC and CMC containing different concentrations of copper oxide nanoparticles. The key feature bands of CMC are revealed in the FTIR spectrum of all samples. Additionally, the figure shows that all samples possess high-intensity bands assigned to copper oxide nanoparticles, which may be due to the structural changes of CMC with copper oxide addition and to the increased concentration of copper oxide. All this evidence supports the formation of a hydrogen bond between CMC and pristine CMC, as well as providing important structural modification information. This table presents the band assignment of the CMC and CMC copper oxide nanocomposite films. As we can see from the table, that the characteristic band of CMC has a strong shift as a result of the addition of copper oxide nanoparticles with different concentration. The shift has been occurred in the position of these bands, confirms the good interaction between CMC and copper oxide throughout these absorption bands. UV visible results. This figure presents the dependency of absorption on the wavelength of the incident radiation. As we can see from the figure that there are 2 absorption bands in the figure. The first absorption band located nearly at 200 nanometer, which attributed to the bye-bye star transition of the CMC. Meanwhile, the second absorption band was redshifted with increasing the concentration of copper oxide nanoparticles, and this is due to the surface plasmonic resonance of the copper oxide nanoparticles. The redshift in the absorption band of copper oxide with increasing copper oxide refers to the decrease in the optical band gap energy. However, this figure presents the spectral distribution of optical reflectance for pure CMC and CMC doped with different concentrations of copper oxide nanoparticles. The figure shows that the reflectance of pure CMC decreased sharply at shorter wavelengths and shows a single peak in the UV region, whereas the reflectance of the films and CMC copper oxide nanocomposite films shows drops somewhat with increasing wavelengths. The reflectance value increases in this region, which may be associated with the increasing roughness of the films due to the addition of copper oxide nanoparticles, which increases light scattering. And also, another reason for this increasing the reflectance is the addition of crystalline nanocomposites, which increases reflectance along grain boundaries. The absorption coefficient of the produced samples was determined using the obtained transmittance and reflectance values utilizing this equation. Plotting the coefficient of absorption against the energy of the incident photons reveals the position of the absorption edge, as can be seen by the arrows in the figure. Extrapolation of the linear part of the curve for all samples to the energy axis gives the value of the fundamental edge. A continuous redshift may be seen in the graph by increasing the copper oxide concentration, and this indicates the decrease in the optical band gap. Additionally, the appearance of 2 absorption shoulders in all the nanocomposite samples confirms the presence of 2 values of the optical band gap. We can use David and Watt equation to know the type of transmission in pure CMC and CMC nanocomposite films. By making the first derivative of the David and Watt equation, we obtain the value of the constant R, which is equal to 2, and it means that the type of transition between the valence band and the conduction band in the pure CMC and nanocomposite samples is an indirect allowed transition. We calculated the optical band gap energy utilizing two models, the Took equation and absorption spectra fitting models. The two models are in good agreement with each other, where they confirmed that all the nanocomposite samples have two transitions, which means that all the films contains two values of the optical band gap. The addition of different weight percentage to of copper oxide to CMC reduces the indirect band gap of CMC, as we see in the table. On this concern, the addition of copper oxides creates localized states inside the band gap, and the transition between such states results in a band gap value less than the HOMO-LOMO band gap. We determine the value of the Auerbach energy using this equation in order to specify the width of the localized states within the forbidden gap. This figure presents the linear relationship between the values of ln alpha and the photon energy for the pure CMC and CMC doped with different concentrations of copper oxide nanoparticles. It can be seen from the figure that increasing the photon energy results in increasing the value of the ln alpha, and hence the relation between Auerbach energy and copper oxide nanoparticles concentration was presented in this figure, and it can be seen that the Auerbach energy increases with increasing the copper oxide concentration, which means that the number of localized states within the forbidden gap increases, and hence facilitating the electronic transition within the forbidden gap. The spectral distribution of the transmittance as a function of the incident wavelength was presented in this figure. It can be seen from the figure that the transmittance increases with increasing wavelengths. However, increasing the copper oxide nanoparticles concentration decreases the transmittance of the pure CMC. As we can see from this table, that the transmittance at 300 nanometer and 600 nanometers was decreased sharply with increasing copper oxide concentration until the transmittance reached to 1.1% at 300 nanometer for the sample containing 8 weight percentage of copper oxide concentration. And this means that this sample was discovered to be the optimal percentage for successfully blocking UV radiation, as it extends to the UVA, UVB, UVC, and also to the visible region. The relationship between opacity and copper oxide concentration was determined using this equation. And we can see that higher opacity number indicates a lower transparency of a film. A sample visualization also for the CMC and nanocomposite films was also determined and reveals that their color gradually changes from transparent to relatively dark gray and finally to black, with the CMC film being more transparent, lower opacity value. Conclusion. Nanocomposite films based on CMC and copper oxide nanoparticles was successfully prepared utilizing the casting method. XRD and FTIR confirmed the formation of the nanocomposite films and the formation of hydrogen bonding between the protons of the hydroxyl group of CMC and copper oxide nanoparticles. The inclusion of copper oxide nanoparticles improves the UV blocking property of the CMC, extended from UV region to the visible region. The localized states produced within the band gap of the CMC reduces the optical band gap of the CMC. The tunable optical characteristics can be utilized in UV blocking filters and various optoelectronic applications. Thank you.
Hello everyone, and welcome to my presentation. First of all, let me thank you all for coming here today. And then I'd like to thank the organizers of this meeting for accepting me in this conference. My name is Bint Khalifa Ahlam, and I'm a PhD student at the University of Tlemcen, Algeria. I work in the field of materials characterization and composites, and my research focuses on chain memory polymers and dynamic molecular simulation. So, as you can see on the screen, our topic today is about theoretical and experimental investigation of the thermal properties of crosslink copolymer based on acrylic monomers. This presentation is structured as follows. First of all, I'd like to give you an overview of shape memory polymers and their applications. Next, I'll focus on materials and methods of characterization. Then I'll go to highlight what I see as the main points of our results in discussion. And finally, I will present the conclusion of our contribution. So in the last years, the shape memory polymers have attracted much attention from researchers due to their good mechanical properties and similar spans. What is a shape memory polymers? Shape memory polymers are a new kind of active and deformable materials which have the capacity to change and recover their initial shapes in response to an external stimulus such as a temperature, light, magnetism, electricity. Shape memory polymers are an exciting area of polymer innovation. The range of application of such material is huge, covering medical, electronics, textile, and others. And the development across all of this area is still ongoing in laboratories around the world. Generally, thermally activated shape memory polymers are the most reported shape memory materials. This last can be characterized by a thermomechanical cycle, which consists of 3 steps. The first step is the shape programming, in which the sample is heated to deforming temperature above the glass transition temperature Tg in order to become flexible and easy to deform. Then the material is deformed to other shapes and cooled below Tg to fix the temporary form. And finally, in the recovery step, the sample recovers its permanent shape when it is heated above Tg. Actually, with the increasing demand for development of new smart materials in different applications, photocrosslink acrylate shape memory polymers have become excellent and promising candidates. This is why in our work, a series of shape memory polymers based on HPMA, hydroxypropyl metacrylate, and isobonyl acrylate were prepared with the same crosslinker concentration under UV irradiation. HPMA is a good useful hydrophilic monomer for various applications, especially in biomedical application. It has an excellent biocompatibility and non-toxicity. Then the analysis was performed using infrared spectroscopy. The spectra of both samples show the acrylic double bond CC, especially in the band of 810 and 1636. This 2 absorption band can be used to describe the polymerization process and evaluate the conversion of acrylic double bond in the resulting networks. As you can see, all the samples show the same decreases in the concerned absorption bands. A very small intensity is observed after 45 minutes, corresponding to the negligible amount of unreacted monomers. However, the evolution of the conversion rate of acrylic also confirms that all the systems show a very fast polymerization rate after 10 minutes of polymerization and start to saturate after 20 minutes. Finally, the highest conversion value between 89 and 98% means the total polymerization of all the acrylic monomers existing in the systems. In the simulation part, the KDJ software is used for the generation of the different systems, for the energy minimization, equilibrating system, and calculating the energy functional forms with the Drayden force field. The different macroscopic and the shape memory properties were done by the LAMP software, and finally the results obtained from the latter are visualized and interpreted by the VMJ software. Then to predict the glass transition temperature of polymer system in molecular dynamic simulation, we often use the theoretical approach called diatomic method. It consists in following the change in the density of the system as a function of the temperature variation. By plotting the values of inverse of the density or specific volume for each temperature, and it is possible to define an estimate of GG value. Combined with the molecular dynamic simulation results, it is verified that the amount of isobornyl acrylate has a significant impact in the shape memory performance, including shape recovery and shape fixity. The system shows a good recovery performance of around 88% when the isobornyl acrylate increase to a certain value, while the HPMA improves the shape fixity of the systems. Finally, it can be concluded that shape memory polymer containing a higher concentration of isobornyl shows the best ability to recover its permanent shape in the recovery step. However, the shape fixity property is quite low compared with the SMP containing a big amount of HPMA. You can find more information on my current research project on my research paper, Enhancement of Shape Memory Properties of Thermoresponsive Copolymer based on HPMA and isobornyl acrylate. And you can also reach me via email. I'm always happy to connect, share information, and discuss. And thank you for your attention.
Good morning, everyone, and welcome to my presentation. First, let me thank you for being here today. My name is Ahmed Rifat, Associate Professor of Applied Spectroscopy, and my presentation is titled Recent Advances in Sensors. Let me start with a brief introduction. Sensors are devices that can detect, quantify, and respond to an input stimulus from the physical environment, and this response is either directly or by converting this input stimulus to a signal for processing by other special systems. The output signals are normally functionally related to the input stimuli, and sensors can quantify almost everything of physical, chemical, or biological concern. So the input stimulus can be light, humidity, heat, motion, chemical reaction, or any other phenomenon. This interesting historical timeline of sensor development technology describing that sensor technology started as early as 105 AD, and progress has been going on since then. If we talk about the classification of sensors, I must say that there are different ways that can be used to classify or categorize sensors. First one is based on their mode of operation, in which they can be classified into passive sensors or active sensors. Passive sensors, as you can see in this photo, they can detect and respond to some type of input from the physical environment, while the active sensor requires an external source of power to operate. If the sensors are classified based on the input-output signal conversion mechanism, they can be classified into number one, thermoelectric sensors. And these sensors produce electrical signal in response to change in temperature, and so they have wide application in medicine. Second one is electrochemical sensors. They produce electrical signal in response to a predefined chemical interaction, as we will see in some of the examples I'll show you later. And as you can see in this photo, the template is prepared for a predefined chemical interaction, and when it happens, the signal is produced. Thermo-optic sensors, they generate signal in response to change in temperature or refractive index, and they are most commonly used, for example, in motion sensors and in these new light bulbs that are switched on automatically when they detect a motion in its field. And the last one is electromagnetic sensors. They generate signal in response to change in conductivity or permittivity, and so they are also subcategorized into inductive type and capacitive type. The inductive type, they detect metallic objects causing disruption in the electromagnetic field produced by the sensor, while the capacitive type detect non-metallic objects having a dielectric constant different from that of air. Before proceeding to the broader and more detailed way of classification of the sensors, it is important to mention that the major and most important part of sensors study is the one addressing its performance, and so specific parameters must be studied in order to assess the performance of a sensor, and these parameters include sensitivity, which is the measure of the change in the output signal of a sensor relative to the unit change in the input stimulus. The second one, and actually one of the most important parameters, is the resolution, which is the smallest amount of a change in the input that can be detected and accurately indicated by the sensor. The third parameter is linearity, which is the detection range that can be graphically represented as a straight line, which is often determined by the calibration curve. Response time and recovery time. Response time is the time the sensor takes to react to a given input stimulus, and it's easy to assume that as the response time is shorter, the better the performance of the sensor. And then the recovery time, which is the time for the sensor to return to the baseline value after the stepped removal of the measured variable, and also the shorter the recovery time, the better the performance of the sensor. And finally, repeatability and reproducibility, they both can be representing the same parameter, except that repeatability is the deviation between measurement in a sequence when the object under test is the same, while reproducibility, although the same as repeatability, except that it also incorporates long time intervals between subsequent measurements. As I said, the more broader and more detailed way of classification of the sensors is classifying them based on their applications. And the first one is the gas sensors. They are designed for and are capable of detecting the presence of many dangerous gases, such as those of toxic or explosive nature, in addition to volatile organic compounds, and are also able to quantify them. And gas sensors are actually very important because they are detecting things that we cannot see with our eyes, and sometimes some gases are odorless, and so here comes the importance of gas sensors. They are commonly designed using metal oxides and the carbon nanomaterials, in addition to thin polymer films and electrochemical solid-state galvanic cells. Let me start with this first example. This paper is titled Enhancement of the Sensitivity and Selectivity of Alpha Ferrous Oxide Nanorod Gas Sensors by Zinc Oxide Nanoparticles Decoration. Here, alpha ferrous oxide nanorods were decorated using zinc oxide nanoparticles, which significantly enhanced the sensing properties towards hydrogen sulfide in terms of faster sensor response and higher intensity sensing response compared to pure alpha ferrous oxide nanorods. As with other nanoparticles, this enhancement is attributed to the increased sensing surface area, which took advantage very small particle size of the nanoparticles, and the formation of more than one depletion zone on the surface of the nanocomposite, leading to decreased resistivity. The best performance achieved was for 300 ppm of hydrogen sulfide at 300 degrees Celsius, with a response time of 164 seconds and recovery time of 173 seconds. As a common trend with the progress in sensor technology, the progress in the production of sensors includes either the introduction of novel materials or preparation methods for the fabrication of sensors, or the enhancement of the performance of the already available materials or compounds commonly used in sensor development. As we can see here, some other examples for gas sensors based on different materials or with enhanced properties. And here are also other examples. And this is the general trend with different types of sensors, including biosensors, gas sensors, smoke sensors, and so on. Here is another interesting example of a gas sensors I would like to show you. In this study titled Nano Architecture of Highly Sensitive Tin Oxide-Based Gas Sensors for Acetone and Ammonia Using Molecular Imprinting Technique. The authors of this study used the molecular imprinting technique by preparing a specific mold on the substrate used at the sensor substrate. They used acetone template and ammonia template, and so the sensor is ready to detect those two specific gases. This sensor showed a very good performance. As a result, demonstrated high sensitivity of about 90% for ammonia, and the detection limit was as low as 600 parts per billion. While for acetone, the sensor device demonstrated high sensitivity of about 77% with a detection limit of 280 parts per billion. The second type of sensors are called temperature sensors. They are currently applied in various fields, including industry, agriculture, and healthcare, in addition to their long-known common applications in the control of different devices such as air conditioners and refrigerators and freezers. Let me start with this first example. The paper is titled Organic Temperature Sensors Based on Conductive Polymers Patterned by Selective Wetting Method. In this study, and relying on the temperature dependence of the electrical conductivity of conductive polymers, organic temperature sensors based on poly 3,4 ethylene dioxythiophene as a conductive polymer was constructed as a temperature sensor. The technology used here is called inkjet printing, and the sensor was fabricated in the form of patterned resistors of PEDOT based polymer. These resistors demonstrated minus 0.75% per degree Celsius temperature coefficient resistant at 23 degrees Celsius, and the temperature coefficient resistant, as shown down here, it is the calculation of the relative change of resistance per degree of temperature change. This sensor showed a very small variation of resistance coefficient of about 4.1%. The results in this method were comparable to those obtained by metal resistors, and these metal resistors were used in this study as references to compare the performance. Results suggested that the fabricated sensors here in this study could cooperate at a long temperature range from minus 10 degrees Celsius up to 80 degrees under normal conditions. And here are other examples of temperature sensors based on different materials or different preparation methods, such as silver nanowires or photonics or fiber optics, and also inkjet printing techniques. The third type are humidity sensors, and these are used to detect and quantify water vapor and representing what is known as relative humidity. They are widely applied in controlling heating, ventilation, and air conditioning systems, and so they serve in different applications, which include preserving pharmaceuticals and controlling preservation condition in museums, greenhouses, meteorological stations, and hospitals. This example from a paper titled High Performance of Colorimetric Humidity Sensors Based on Minerals. In this study, the authors used bromothiamine blue as an indicator for humidity, titanium dioxide, palygorskite, and molite were chosen as the host of the colorimetric humidity sensor. There was a readable response by BTB, titanium dioxide, that was observed to the RH of 11, 43, and 75% at 1 minute at 25 degrees Celsius. The BTB palygorskite demonstrated a better response, especially at lower values of relative humidity around 11%. Results indicated that the performance of the sensor was clearly affected by the surface area, and so the cover density of BTB and water absorption would significantly enhance their performance. And you can see here the change in color, the change in the color of bromothiamine blue in response to change in the value of relative humidity. These are other examples of humidity sensors based on gold electrodes, based on laser-induced graphene porous electrodes, and all carbon-based flexible humidity sensors using cellulose nanofibers. The fourth category of sensors is represented by smoke sensors, and when talking about smoke, we are essentially talking about air pollution. And so air pollutants represent a class of the most hazardous pollutants to human beings and animals owing to the toxic effect they pose on skin and eyes, as well as other living tissues, especially, as I said, those exposed, normally exposed to air pollutants. And over the past decades, special attention has been given to maintaining the adequate quality of urban air, because air pollution, as we all know, has reached dangerous levels to human health. The most common causes of air pollution are unburned gases such as carbon monoxide and nitrogen oxides and sulfur oxides, which are considered the major sources of air pollution. And the main sources of these gases include industries, vehicles, aircrafts, fumes, and the petrochemical plants. In this study, a cell mean diameter sensor for fire smoke detection. In this study, the authors wanted to introduce a new fire alarm to avoid false fire alarms that might be activated by non-fire aerosols. So they developed a novel Salter mean diameter sensor that is based on dual wavelength, 450 nanometer blue light and 950 nanometer infrared light instead of smoke concentration for fire detection. I just must clarify, Salter mean diameter is the average of particle size, is defined as the diameter of a sphere that has the same volume surface area ratio of a particle of interest. An extra correction has been introduced by the authors of this study by adding an extra correction channel that has been added to the fabricated sensor in order to quantify aerosol samples with varying particle size and different refractive indices while maintaining a low error of measurement. And so it was inserted as a reference in order to separate between real fire alarms and false fire alarms. Results of this study confirmed the ability of the sensor to promptly activate the alarm to fire smokes while avoiding false fire alarms caused by non-fire aerosols. Another 3 examples of smoke sensors, as you can see, gas smoke sensors based on breach 58 functionalized beryllium oxide nanostructures, and another one based on flexible and porous graphene composites, and a third one highly sensitive and selective room temperature smoke and humidity sensor based on chemically grown porous hydrangea type bismuth molybdate. The last category of sensors in this classification are biosensors, which are devices that contain a specific receptor molecule ready to detect and to respond to a specific measurement, and a physicochemical transducer is used to generate the measurable signal relative to the input stimulus. Biosensors date back to 1962 when the first blood gas screening biosensor was developed in order to monitor blood gases during surgeries. Nowadays, the most frequently used forms of biosensors which are very simple, like home pregnancy tests and the glucose detectors, with strong modification, increasing every day to introduce new classes of sensors for wide ranges of application, including nucleic acid tests, food analysis, and drug detection. With the recent progress in biosensor technology, it essentially helped in the introduction of novel, advanced, robust, accurate, and fast responsive systems, having the ability to detect changes in the levels of the specific measurement under study or that's required to be detected, associated with the presence of a certain disease, and so they can provide faster diagnosis and consequently a faster treatment of many diseases. In this example, this paper is titled "The Biosensor Composed of Integrated Glucose Oxidase with Liposome Microreactors Cytosine Nanocomposite for Amperometric Glucose Sensing," and so it has a potential application in monitoring of blood glucose. It's a biosensor composed of glucose oxidase liposome microreactor and a glassy carbon electrode modified by chitosan. The results of this study reflected a broad linear range of detection, starting from as low as 0.01 millimolar per liter up to 10 millimolar per liter of glucose, with a very good detection limit of as low as 1.32 micromolars. Results also indicated that the activity of the electrodes is relatively low, and so it has high sensitivity to glucose, as obtained by Michaelis-Menten kinetic model, indicating better affinity between the enzyme and the substrate. The authors concluded that this simple biosensor shows a great potential in rapid and inexpensive analysis of glucose with excellent reproducibility and stability. And as you can see here in this table, there is a comparison between the results obtained in this study and the results reported in other studies. You can see the limit of detection in micromolar. You can see here how low is the limit of detection in this study, and the linear range, how long is the linear range compared with other studies. And here are additional examples of other biosensors, and I must say that the biosensor is a very large category of sensors because of the large number of materials that can be used in the fabrication of sensors, and also the big variety of substances or measurements that requires to be monitored and measured. So like here, for example, additional examples for the detection of glucose, and also because of the pandemic that has been ongoing for 3 years now, are sensors for COVID-19 and also for the detection of some viruses like Zika virus. And here is also a biosensor for the detection of uric acid, and here for the detection of amino acid L-tryptophan. And speaking about coronavirus, it is important to mention this very interesting example for a biosensor that has been fabricated for the detection of SARS-CoV-2. The paper is titled "All Solid-State SARS-CoV-2 Protein Biosensor Employing Colloidal Quantum Dots Modified Electrode." SARS-CoV-2 is the name of the virus that causes coronavirus infection or COVID-19. And the authors of this study used electronic labeling of protein molecules and employing colloidal quantum dots modified electrodes. So this study is based on the very specific interactions that happens between the antigen and the antibody of SARS-CoV-2. Results confirmed the detection of the characteristic peak resulting from this interaction that was detected by the colloidal quantum dots modified electrode. And in order to more accurately and more reliably assess the performance of the biosensor, it has also been tested on real serum specimens from COVID-19 patients, and the results reflected the ability of this biosensor to quantify SARS-CoV-2 antibodies with 93.8% correlation coefficient, which is a very acceptable performance when compared to ELISA test. Results also demonstrated the ability of this biosensor to discriminate COVID-19 from normal samples with accuracy of around 90%. Finally, and to conclude this presentation, this review presented the recent advances in the development and performance of gas, humidity, temperature, and smoke sensors, as well as biosensors which are applied in different fields and for various applications. And because of the increasing challenges recently worldwide, such as climate change and the emergence of outbreaks of some diseases, uh, the continued progress in sensor technology is highly required and is eventually beneficial, and this can be done by the introduction of new application-specific cost-effective sensing materials, as well as improving the fabrication methods and enhancing the sensor's performance. Thank you for your time and your attention.
Hello everyone, it's a pleasure to be here with you at this important conference. I am Dr. Hinda Izzet, a researcher in the Nanotechnology Unit at the National Research Institute of Astronomy and Geophysics. My presentation is titled Studying the Optical and Thermal Properties of Ketosene Zinc Oxide and Ketosene Zinc Oxide Graphene Oxide Hyper Nanocomposite. Let's start with outlines divided into introduction, aim of the work, sample preparation, result and discussion, and finally our conclusion. As known, nanotechnology defined as the design, fabrication, and utilization of structures, materials, and devices by controlling shape and size less than 100 nanometer. The significance of this technology is determined by its use in a variety of fields, including environment, agriculture, biotechnology, electronics, energy, medicine, and aerospace. According to my specialization in space applications, we focused on nanotechnology for aerospace materials because the materials for space application should have unique properties to suit the space environment, such as low weight, high resistance to extreme condition, and high strength. Such materials are used for various applications, including sensor, optoelectronic material, coating, UV sensing, X-ray shielding, and so on. Nanomaterials are classified as organic, inorganic, and hybrid composites. Organic, such as carbon-based material, which have a significant property as functionality, beside enhancing mechanical, electrical, and thermal stability. Inorganic, such as metal oxides, which have a significant property as functionality, large surface area, and narrow band gap, beside enhancing optical, electrical, and sensing properties. Hybrid nanocomposites defined as a combination of two or more organic or inorganic components, one of them in nanoscale. There are different types of nanocomposites divided into polymer-based material and non-polymer-based material. Polymer-based nanocomposite could solve many of the weight-based and process-based problems plaguing the space industry and offer new capability for future systems. There are two different types of polymers, natural polymers and synthetic polymer. Natural polymers are preferred recently according to the use of green technology, which defined as the synthesis or hybridization of nanomaterials with natural bioactive compounds. This is a low-cost, eco-friendly, easy to manage, and non-toxic technology. So the aim of our work is to use green technology to prepare hybrid composites with simple, eco-friendly, and low-cost technique, study the impacts of nanofillers on the physical, chemical, and thermal stability of new composites, study the optical and thermal properties of the produced composite. So to achieve our aim, we prepared our samples as follows. For nanomaterials preparation, the precipitation method was used to make zinc oxide with zinc acetate as a metal salt and sodium hydroxide as a precursor. Also, graphene oxide was prepared using the Hammers methods using a mixture of sulfuric acid and potassium permanganate on graphite. For ketosane zinc oxide nanocomposite, we prepared 5 different percentage of zinc oxide with ketosane from 10% to 50% of the weight using casting method by soluble ketosane in distilled water with acetic acid, then adding zinc oxide to the solution before casting. For ketosane zinc oxide graphene oxide nanocomposite, we prepared 2 different samples with 2 different methods, casting as mentioned previously, and one put method. The one put method was used by combining soluble ketosane, soluble zinc acetate, and soluble graphene oxide as a mixture, then adding sodium hydroxide drop by drop to achieve a pH of 10. All samples were conducting to a very high-tech techniques to show the effect of hybridization on ketosane polymer, and now we will present the result and discussion. To confirm the formation of zinc oxide, we used different characterization tools, including Fourier transform infrared, which study the molecular structure of the compounds. FTIR of zinc oxide showed that 2-band characterized and confirmed the deformation of zinc oxide at the nanoscale. Also, UV visible spectra of zinc oxide nanoparticle observed at a peak at 376 nanometer. Then, prepared zinc oxide also analyzed by scanning electron microscope and transmittance electron microscope to study the morphology of them, which indicates that the particles are mainly spherical in form and aggregates into large particles morphology with particle size from 20 to 50 nanometers. For graphene oxide, FTIR spectra shows the absorption bands of C double bond O stretch of the carboxylic group and the CC of graphene sheets in 1713 and 1575 cm-1. In addition, absorption band appeared at 1421 cm-1 was attributed to OH function group. COC stretching and CO vibrations could also be due to the carboxylic acid and carbonyl groups located at the edges of graphene oxide at the 2 absorption bands around 1218 cm-1 and 1049 cm-1. Then the UV visible spectra of graphene oxide showed a maximum absorption peak appeared around 129 nanometer owing to pi-star atomic CC bond transition, and shoulder absorption peak around 341 nanometer due to n-pi-star aromatic bond O bond transition. Also, graphene oxide image showed the surface randomly aggregate as similar thin sheets with separate edges, wrinkled surface, and folding. For ketosane zinc oxide samples characterization, according to the FTIR spectra, the main features of the molecular structure of pure ketosane are shown in the figure, and the main characteristic bands of ketosane are listed in the table. The presence of zinc oxide effects on the ketosane spectrum by shifting bands to the higher wave number, beside the disappearing of C double bond O band with appearing of zinc oxide band around 450 cm-1, which confirmed the interaction between zinc oxide and ketosane through NH2 group, which make a change in molecular structure from acetyl to diacetyl ketosane. Ketosane zinc oxide samples were also subjected to nuclear magnetic resonance measurements for proton NMR. The main characteristic peaks of ketosane protons were appeared as shown. For ketosane zinc oxide, the peaks were suffering from broadness and all the peaks related to completely diacetyl ketosane, with disappearing of CH3COO group and NH changed to NH2. In addition, protons of NH2 disappeared, indication for coordination between zinc oxide and ketosane through it, and the broadness of the peaks is an indication for metal presence according to paramagnetism, which confirms the coordination of zinc oxide with NH2 group as the FTIR result indicated. Also, scanning images for ketosane and ketosane zinc oxide samples showing that ketosane surface have a small pores that distributed ununiformly on composite surface. The pore size increased with addition of zinc oxide, and with increased the weight percentage of zinc oxide, the pores became less with appearance of white spots that regarded to zinc oxide which accumulate on ketosane surface. The FTIR spectra of the hybrid composite ketosane zinc oxide graphene oxide with the two different methods, casting and one put, shown in figure. The characteristic ketosane bands appeared. In addition, a new band appeared at 1657 and 1652 is assigned to the carboxylic group from graphene oxide and is downshifted because of hydrogen bonding between the graphene oxide and zinc oxide. There is a shift in NH2 group to higher wave number 1549 and 1560 cm-1. These shifts reflected the interaction between ketosane and zinc oxide through NH2. Then a relativity shift to higher wave number for zinc oxide band around 472 and 474 cm-1, which attributed to the carboxylic functional groups formed by the interaction of zinc oxygen carbon. Also, scanning image for the composite prepared by casting method showed a white spots and accumulate in some region on the surface. However, for ketosane zinc oxide graphene oxide method, there is a small white rod shape and other accumulate on ketosane surface, which regard that there are many interactions between ketosane zinc oxide and the graphene oxide edges. The UV visible spectra of ketosane doped with different weight ratio of zinc oxide and ketosane zinc oxide graphene oxide showed a maximum absorption peak at 206 nanometer of ketosane. For ketosane zinc oxide, there is a shift in the peak of ketosane towards longer wave number, according to the appearance of zinc oxide. The presence of pi delocalization along the polymer chain has been stated due to strong change towards longer wave number, and there is a weak peak appeared at 350 nanometer, increased with increasing filler, which indicate and confirm the interaction between ketosane and both zinc oxide and graphene oxide. Also, one put hypercomposite showed that there is an absorption peak at
to 152 nanometer attributed according to the interaction between ketosane, graphene oxide, and zinc oxide. Also, the absorption age defined by the excitation of electron by incident photon from lower energy to higher energy state, which is estimated by exploration of the linear part of absorption coefficient with photon energy h nu. Absorption coefficient is determined from the following relation. As shown, the relation between absorption coefficient and photon energy for prepared sample, the values of absorption age decreased compared to pure ketosane, and the lowest value was for one-put composite. Also, according to correlation between ln give band-tail energy and its value, showing that ketosane doped with both zinc oxide and graphene oxide give higher value of band-tail energy compared to has high conductivity. Values of both direct and indirect band gap energy calculated from extending the straight line from the linear part of the curve to the h nu axis. As seen, with increasing the filler, values of direct and indirect band gap energy decreased compared to pure ketosane, and it has a lower value for ketosane doped with zinc oxide and graphene oxide. Previous results showed that ketosane zinc oxide graphene oxide prepared one-put hybrid method reduced the order and is the best preparation method for the use of ketosane zinc oxide graphene oxide as of thermal gravimetric analyses were conducted to study the thermal behavior of prepared samples. These results show that ketosane zinc oxide nanocomposite and ketosane zinc oxide graphene oxide hybrid composite had higher residual mass percentage relative to the presence of zinc oxide and graphene oxide due to the rise in temperature. In addition, certain improvement in the degradation behavior of composites found relative to the ketosane changed from 22 to 79%, which could decrease the degradation of ketosane with increasing the filler, and the highest percentage was for one-put nanocomposite. So, ketosane zinc oxide nanocomposite exhibits significant enhancement in thermal stability compared to pure ketosane. Also, ketosane zinc oxide graphene oxide hybrid composite one-put exhibit more thermal stability than all. Finally, we can conclude our work as zinc oxide graphene oxide hybrid nanocomposite were prepared with different methods, casting and one-put, and verified using FTIR and NMR spectroscopy, which confirmed that the interaction occurs through NH2 function group of ketosane with zinc oxide and the carboxyl group of different shape and particle size of zinc oxide effect on the electronic and optical properties of nanocomposite. Also, one-put is the ideal method for preparing ketosane zinc oxide graphene oxide as optoelectronic material. Finally, I would like to thank you all, and I am waiting for any questions.
Assalamu alaikum. Do you think we hear a lot about ketosane or not yet? I think not yet. Now I'm talking about developing two ionic derivatives of ketosane. I'm talking about their structure and dynamics relationship. Ketosane, most of us worked already about ketosane, and it contains mainly in its repeating unit cosamine, and its natural product comes from chitin of the shrimp, chitin shell of the shrimp, And because of some properties, it is antibacterial and it is biodegradable, and it is widely used in biomedical application. Now, imagine if we are able to put a charge. Imagine if we are able to put a charge on chitosan. Actually, that will open or widen the application of chitosan, especially in bioelectronic application, meaning that devices which are in contact with the body or human body, like these biosensors or even some chips inside the body. And how chemists do that? Chemists do that. They dissolve chitosan in acetic acid or even hydrochloric acid, and after that they let it to interact with cyanamide, and then I say, do you see my? Okay. Then some cationic group is attached to the amide group in the chitosan. This group, we call it guanidinium group. And afterwards, depending on the acid we dissolve it, we have 3 ions of acetic acid, of acetate group, or chlorine group. And hereafter, I will call my derivatives chitosan-based acetate or chitosan-based chlorine. We checked the structure of our product by FTIR, and in chitosan we saw already the characteristic bandings of the chitosan, and for these chitosan or for our derivatives, we see the change in the intensity only of the carbonyl group, and this is change or the increase of the intensity. Meaning that it attached already this guanidinium group. For simple analysis or gravimetric analysis, we see our derivatives is most stable than the chitosan itself. We checked the surface of the products by scanning electron microscope, and we found that the surface is rough with some kind of porosity, and looking for with the transmission electron microscope, we see agglomerated particles of diameters roughly 50 nanometers. For dynamics, we applied dielectric spectroscopy to see the molecular dipolar relaxation. And for chitosan, like any polysaccharides, we see that such a process. This process is, we call it beta process, and it shows some kinds of local motions inside the repeating units. What about the derivatives? Oh, sorry. The derivatives for this chitosan-based acetate group, the intensity of beta process is diminished a bit, and while that is based on chlorine groups, it is roughly depleted. This meaning that the ions moving around in chlorine and the chitosan-based chlorine group, and it is already masked the motions of the local of the liquid motions. If we check the conductivity, chitosan, like any insulating polymers, it has something like 10 minus 8 and downwards with temperature. And after that, for chitosan-based acetate, it is more or less similar to chitosan. While for chitosan-based chlorine, it is increased something like 4-ordered of the conductivity. We picked already the conductivity, DC conductivity. We found that they are, all of them are Arrhenius like temperature dependency. How we could interpret that? Actually, we put an interpretation here. If we imagine the chain of the chitosan like a linear chain, or simply it is linear polysaccharide, but I draw it as a linear chain. and a state group is moving around like this, and on the other side, chlorine ions are moving around. Acetic groups is mostly interact with the chain, and resides less on the chain. Sorry, it resides more time on the chain. And chlorine groups on the other side, it resides to the chain at a short time. So this meaning it moves all the time, meaning it carrying current. My conclusion, we are able to prepare two derivatives of chitosan. These two derivatives show already one relaxation process, and we suggest or we recommend our products as a green technology. In the end, I thank you all.
I am Dina Izzat. I have a PhD in solid state physics in Shams University. The research will be the influence of addition of molybdenum trioxide nanoparticle on the structural and optical properties of cellulose film. The contents will be introduction of aim of work, result and discussion, conclusion. Polymers has too many properties like low cost, flexibility, good mechanical strength, high resistivity, high strength, easy processing. From all polymers, cellulose acetate has too many properties which make it interesting to study. Like it have high solubility, perfect insulator, high hydrophilicity, high optical transparency, and low cost. Transition metal oxide has many properties like its electrical, magnetic, and color properties. From all transition metal oxide, molybdenum trioxide has too many properties like it has electrochromism properties, wide band gap, good optical and catalytic properties, and it has photochromism properties. Many research have been made in cellulose acetate composite, and the researcher who observed that cellulose acetate optical and electrical properties were developed by the addition of another material. So our aim of work is to prepare cellulose acetate film and cellulose acetate film blending with different concentration of molybdenum trioxide nanoparticle, studying the effect of addition of molybdenum trioxide nanoparticle on cellulose acetate properties, studying the effect of addition of molybdenum trioxide nanoparticle on cellulose acetate structure. We use casting method as to prepare cellulose acetate film by using magnetic stirrer to dissolve cellulose acetate powder in dense solvent. Then we casting the solution in petri dish and waiting for some time until it getting rid of air bubble. Then we put the film on the dryer until the films dried. Then we use them in order to study different properties of cellulose acetate. The crystallinity of the film were studied by using X-ray diffraction. We observed that the pure cellulose acetate have two homes, which indicates the amorphous nature of pure cellulose acetate. Upon adding different concentration of molybdenum trioxide nanoparticle, we observed that three homes observed, appeared, and upon adding more concentration of molybdenum trioxide nanoparticle, we observed that this peak's intensity was increased, which means that upon the addition of molybdenum trioxide nanoparticle, the cellulose film began to partially crystallize, and its crystallization were increased by increasing the metal oxide concentration. We use strain size plot method in order to calculate the metal oxide size, and by draw a relation between d square beta cosine theta and db beta cosine theta square. From the slope we get the particle size, which we see that it is 92 nanometer, which indicates that the molybdenum trioxide is in nano size after we put it in the film. We study the optical properties. We observed that transmittance, we draw the transmittance as a function of wavelength, and we observed that the transmittance of pure cellulose state was too high, and it is decreased with increasing the molybdenum trioxide concentration. Also, we draw a relation of reflectance as a function of wavelength, and we observed that the reflectance increased with increasing the molybdenum trioxide nanoparticle concentration. From this relation, we calculate the absorption coefficient, and we observed that it is increased also by increasing the molybdenum trioxide nanoparticle concentration. We calculate the molar extinction coefficient from this relation, and draw as a function of wavelength. And from Gaussian fitting, which is with the red line for the molar extinction coefficient, we calculate the electric dipole strength Q square and the oscillator strength F, and we observed that the electric dipole strength was increased by increasing the molybdenum trioxide nanoparticle. We use Stokes equation in order to calculate the type and band gap of cellulose state. First, we draw a relation between H mu and alpha H mu by alpha H mu per H mu, and from the slope of this relation, we get the transition type, which indicated to be indirect transition. And from Stokes equation, we draw a relation between H mu and alpha H mu power half, and we observed there was two band gaps, onset gap and homolomo gap, which observed to decrease with increasing the metal oxide concentration. We calculate Arbach energy from Arbach equation, and we observed that the Arbach tail was decreased with increasing the concentration. From this equation, we calculate the refractive index and draw it as a function of wavelength. And we observed that the refractive index increases with increasing the concentration of metal oxide. We use free single oscillator model in order to calculate the oscillation energy, dispersion energy, finite dielectric constant, and lattice dielectric constant, and free carrier concentration. From the relation between h mu square and 1 over n square minus 1, we can calculate the oscillation energy and dispersion energy, which we can see here. From the relation of n square as a function of lambda square, we can calculate lattice dielectric constant and the free carrier concentration. We observed that there is a difference between lattice dielectric constant and high dielectric constant, which indicates that there is free carrier concentration. We calculate also n over m, which observed to be decreased with increasing the molybdenum trioxide nanoparticle concentration. We studied complex dielectric constant epsilon 1 and epsilon 2 and tan delta as a function of wavelength, and their shapes. We studied damping coefficient from this equation and from the relation between epsilon 2 as a function of lambda cube. From the slope we get damping coefficient, which is indicated here. Conclusion: X-ray diffraction result indicates that the sample partially crystallized after addition of molybdenum trioxide nanoparticle to indirect energy band gap were observed and showed a decrease with increasing nanoparticle concentration. A difference between the value of epsilon infinity and epsilon L was observed due to contribution of free carrier concentration. The large decrease in optical transmittance is desirable for Windows application. Also, the appearance of an edge separates the absorption region from transmission. One recommended it as a good optical filter material. Thank you.
Hello everyone, it's my pleasure to introduce this work in the first International Conference on Molecular Modeling and Spectroscopy. This work for the authors Nagla Shaheen and Riham Kamal, Physics Department, Faculty of Women, Ain Shams University. Our talk today will be about the effect of copper oxide on the structural, optical, and electronic properties of PVB experimental and DFT study. Let's start with our contents: introduction, aim of the work, preparation method, characterization techniques, results and discussion, and conclusion. Introduction. Polyvinyl pyrrolidone, which is abbreviated as PVB, is a thermoplastic polymer, and this is the molecular structure representing PVB. It has a number of advantages like non-toxic, have high molecular weight, and water soluble. Because of its low toxicity and high water solubility, it can be used in pharmaceuticals, medicines, cosmetics, biomaterials, and coatings in food industry. The major aim of this study is to control the optical properties of PVB to increase its commercial and technological applications, and to analyze obtained solutions by FTIR and UV visible spectrophotometers, and also to make a connection between theoretical and experimental work. For the experimental work, The nanocomposite solutions based on BVB and copper oxide were prepared utilizing the solution casting method according to this table. However, all the calculations were carried out utilizing density functional theory as implemented in Gaussian 09 package at Spectroscopy Department, National Research Center. The prepared nanocomposite solutions were characterized utilizing FTIR spectrophotometer and UV visible spectrophotometer, and finally molecular modeling. This figure presents the FTIR absorption spectra of pure BVB and BVB doped with different concentrations of copper oxide nanoparticles. As we can see from the figure and table that the principal bands and functional groups associated with BVB are seen in the absorption spectra. However, the band assignment of pure BVB and BVB copper oxide nanocomposite solutions was obtained in this table, and it's clear from the table that the appearance of the copper oxide stretching vibration in the region above 400 cm -1, confirming the formation of the hydrogen bonding between copper oxide and BVB and the formation of the nanocomposites. This figure presents the dependency of absorbance and the transmittance spectra on the wavelength of the incident radiation and also on the copper oxide concentration. As we can see from this figure that there is absorption band at nearly 234 nanometer, which is due to the N by star transition, and the intensity of this band increases with the increasing concentration of copper oxide nanoparticles. Also, it can be seen that there is a broad absorption band nearly 722 nanometer, which reflects the existence of surface plasmonic resonance peak, which appear as a result of the addition of copper oxide nanoparticles. However, this figure represents the transmittance of pure BVB and BVB copper oxide nanocomposite films. As it can be seen from the figure that BVB has a very high transmittance, reaches to nearly 93% at a wavelength of 400 nanometer, and it steadily increases towards higher wavelengths until it reaches its maximum value at nearly 8 nanometers. The transmittance drops quickly at lower wavelengths and gets close to zero at about 250 nanometer. The basic absorption of light, which is brought on by the excitation of electrons from the valence band to the conduction band, is what causes the dramatic reduction towards the UV area. Increasing the copper oxide concentration results in a decrease in the transmittance of BVB until it reaches to 1% for the sample containing one weight percentage of copper oxide nanoparticles. This confirms that it can be used as a protective layer from sunlight, as the transmittance decreases to 1% in the three spectral regions under study, although we mean that UV and the visible and near IR regions. As we know that the analysis of the absorption coefficient has proven to be crucial in predicting any changes in the electrical band structure of polymeric materials. Also, it is well known that investigating the fundamental absorption age reveals important details about the optical band gap of the polymers. And as we can see from this figure that the absorption coefficient varies with the incident photon energy, and also that BVB and the nanocomposite solutions have only one absorption shoulder, and which would shift it to the lower energy region by increasing the copper oxide concentration, and this predicted the changes in the optical band gap energy. We determined the values of the direct and indirect optical band gap energy using the equation. As we can see from this table that the variation of alpha h nu power 2 and alpha h nu power half with the incident photon energy shows only one absorption shoulder, which means that all the samples have only one absorption peak. Extrapolation of the linear portion of all curves to the x-axis gives the values of the energy of the prepared samples. As we can see from this table that increasing the copper oxide concentration results in a decrease in the optical band gap energy, direct and indirect allowed optical band gap energies. The decrease in the values of the optical band gap energies may be as a result of the creation of the localized states within the forbidden band gap and the transitions of electrons between these two levels. We determine the value of the Orpach energy in order to determine the width of the localized states within the forbidden band gap using this equation, and also by plotting ln alpha as a function of the photon energy. As we can see from the figure that the values of the Orpach energy can be obtained by calculating the reciprocal of the slopes of the linear portion in the higher energy area of these curves. As we can see from the table that increasing the concentration of copper oxide leads to an increase in the values of the Orpach energy. This causes an increase in the number of traps and a decrease in the visibility of energy transitions, which lowers the values of the optical band gap energy. According to David and Mott, the filling process caused more defect states to exist within the polymeric matrix, which is why Orpach energy changed. Modeling was utilized to study the mechanism of interaction between BVB and copper oxide nanoparticles. In building our model molecules, we suppose that three units of BVB was supposed to interact with only one copper oxide molecule. The possibilities of interaction between BVB and copper oxide is that proceeds through the C double bond O group present in the 3 units of BVB, which means that the interaction proceeds throughout the terminals and the middle unit of the BVB. As we can see from the table that the calculated total dipole moment and HOMO-LOMO band gap energies of the different interaction mechanisms results in a change in the total dipole moment and HOMO-LOMO band gap energy. Also, it can be seen that the interaction of copper oxide with BVB chains can be processed through the metal atom of the copper oxide and the oxygen of the BVB, and also through the oxygen atom of the metal oxide to the oxygen of the C double bond O group of the BVB. As we can see from the figure from the table that the interaction processed throughout the terminal unit of the BVB and through the oxygen atom of the copper oxide molecule has the lowest HOMO-LOMO band gap energy, which is the most probable interaction to occur, as it has only slight energy to occur in comparison to other proposed structures. Also, we studied the molecular electrostatic potential of BVB and BVB copper oxide model molecules in order to study the reactivity of copper oxide and the effect of copper oxide on the BVB reactivity. We know that the molecular electrostatic potential maps can be described by following a color maps ranging from the high electronegative regions as the red regions to the neutral regions, which are recognized as yellow regions. As we can see in this figure, which represents the molecular electrostatic potential of BVB, that only red regions are presented around the oxygen atom of the BVB structure, which is confirmed our postulate in the last slide that the interaction between copper oxide and BVB can proceed through the C double bond O group of the BVB model molecule. However, the interaction of copper oxide with BVB in the 4 different positions, the intensity of this red color increases in the 4 positions, which confirms that the reactivity of BVB was enhanced by the interaction with copper oxide. And this results confirming the total dipole moment and HOMO-LOMO band gap energy results. Conclusion: using the solution casting approach, different weight percentage of copper oxide nanoparticles have been incorporated into the BVB solution. FTIR results confirmed the formation of hydrogen bonding between copper oxide and BVB. Also, it was discovered that the absorption edge was shifted to the lower energy region. Moreover, it was discovered that the TOX model was essential for identifying the different kinds of electron transition. The optical band gap energy was found to decrease with increasing copper oxide concentration for the direct and indirect transitions. Theoretical results also indicated that HOMO-LOMO band gap energy decreased upon the interaction of copper oxide with BVB and increasing the total dipole moment values. These findings demonstrate how experimental and theoretical work can be used together to gain understanding of how molecular structures affect where it can reveal unexpected properties of nanostructures. Also, this results confirms that the prepared solutions of BVB and copper oxide can be used as a protective layer in food packaging industry or in sunscreen industry. Thank you.
So thank you very much. So I think now it's a time for open discussion. I invite Hind Izzat and Rania Badri. Dina is here, and Dr. Fathiya. Please come here, okay? Dina Izzat. شوف لنا دينا برا. خليك انت عارف. شوف لنا دكتورة دينا برا لو سمحتم. تعال تفضلوا. عليكم السلام ورحمة الله وبركاته. تعال تفضل. So I think in the first session it was a combining between the theoretical method based mainly on quantum mechanical calculation and some kind of molecular spectroscopic tools, also with some class of optical measurements. Let me start with Rania Badri. I would like to ask you, actually you are working with experimental tools. Why you need to work with molecular modeling?
Actually, in this work, we use molecular modeling for a number of reasons. Firstly, if I wanted to the mechanism of interaction between polymers and metal oxides. So we started with molecular modeling in order to what happens when adding different metal oxides to the studied polymer. And so in this case, we use molecular modeling to predict the behavior of the materials under study, and also to facilitate the interaction and consuming time, which it's save chemicals and time and prevent the waste of the chemicals by repeating experiments many times. So molecular modeling can be used to predict the interaction and to confirm the experimental results, and also to make the experiments that ethically cannot be performed on humans and animals ethically.
Okay, so actually I could got the mechanism from literature. So why you do the mechanism by yourself?
To confirm the results of FTIR absorption spectra and XRD, as we know that in our work, we concluded by molecular modeling, the interaction between metal oxides and polymers can occur throughout the formation of a hydrogen bonding. And this occurs by confirming the FTIR absorption spectra, as it confirms the shift in the absorption bands confirms that a strong interaction has been occurred through the formation of a hydrogen bonding.
So actually in our work, when we start to make electronic properties of material, if you are going to consult theoretical methods, even you start in the beginning to make your molecule and make your calculation to drive your experimental way. Or you study your experimental work and you need to make some kind of mechanism, what's going on the molecular level, for example, or atomistic levels. That's why you could use molecular modeling in the beginning of the work or even in the end of your work, depends on what you need from modeling. So actually this is an example for combining experimental and theoretical aspects in physics, okay? Seems to be that I'm confused a little bit because she's working in natural polymer with metal oxide, for example, for optical properties, but you consult the same structures, but for space. So how can I differentiate between two approaches?
In our work, we focused on using light material to be used for aerospace applications and enhanced for electrical and optical applications with the unique properties of suit aerospace environment. Reduced the degradation of the material and enhanced to be used for a long time.
Okay. So like what we present in our presentation, that we are tuning materials with nanoscale metal oxide, for example. So tuning the material means that you're driving the application of your material toward a certain direction. That's why you can use certain polymer, for example, in optical properties, but another tuning could drive the same polymer toward space application because you can prevent or inhibit the degradation of the material, for example, to be anti-corrosive and so on. So we have another way, and then I will start to make an open discussion that Dr. Fathi has really a unique work, because actually when I work with Fourier transformation infrared, I'm using static parameters. If I'm working with biophysics, for example, I got the sample and dry the samples and use it while it's dead. But actually, she is working with dynamics. So dynamics is consulting time, but in conventional infrared, time is 0. So how can you tune this? How can you work with infrared and your dynamics work? Okay.
Yes, actually, in infrared spectroscopy, you are looking for functional group and you follow it up. Where is the structure? If the structure is okay or not, or you have some impurities. To see some dynamics from infrared spectroscopy, you might follow a functional group, and by heating up and see if it is shifted around by temperature or doing some changing, and you can pick it up, this change with temperature, and you say this vibrational motion, it is already doing some fluctuations. While in another technique, I use dielectric spectroscopy. Dielectric spectroscopy is sensitive to the dipole moment presence in the sample, and to put the electric field around, and this dipole moment moving a bit, but you must to keep your linear response regime, meaning you apply a little bit electric field, and you see the fluctuation of the dipole following this field, and once you are already in linear response regime, this fluctuation of the dipole moment these fluctuations of the dipole moment, you can say this is my molecular fluctuation. In other techniques, even let me say neutron scattering or other techniques like NMR relaxation, you follow for example, in NMR relaxation, you follow the fluctuations of the magnetic moment. You put a magnetic field and you let the magnetic moments presence in the sample, you let it to move, or you let it to follow the magnetic field, and you measure the relaxation of these magnetic moments, and you see by some series you will transfer it to fluctuations of the molecule itself. And in dielectric spectroscopy, this is my let me see, my favorite, because it is already easy for me to measure and to apply some models around. If the sample contains more uncharged or ions moving around, I hardly see some molecular fluctuations. I have to do my best to extract some molecular relaxations from my spectrum. But that's all. I hope I answered well.
Actually, she got her PhD from Germany. That's why she is consulting time during the work in the sample. So from static to dynamic, it's not easy. At least you need complicated techniques to work with, but they can do it with dielectric spectroscopy here, which is a very interesting technique. I hope to extend this work in future, inshallah. And now let's open the stage to your questions. We are ready to answer because all the speakers are here, okay? حد عنده أسئلة من حضرتك؟ دكتور علاء. So please come here. Let's say a couple of words in Arabic. اسأل سؤال عدل أحسن مش هغليك.
My question is very simple. If we say another word in Arabic, For answering one question, I get one bonboni, please. Sorry, عشان أرد سؤال لازم آخد bonboni.
طلبات فئوية. Please.
Dr. Fathia, you used ketosane and doped with chlorine. Ketosane and doped with chlorine.
Not doped, it is ions of chlorine is moving around.
Okay, to use as a bioelectronic system. Okay, yeah. Chlorine outside the stomach is toxic.
Yes.
So how you can use it with biological material? This is my question.
Thank you for the question, but I want to say this question we will answer it in the second part of our work. We will do some let me say some biodegradable testing or something like this. We suggest a compound which is natural, let me say, or natural in its base, and it has some electronic properties, and we say for the biologists that's it, and they will do their best.
So you could avoid toxicity.
Yes, yes.
Okay, thank you.
خلاص كسبت الغدا كده. So another question, if any? تفضل تعالى عشان الصوت يطلع في ال. تفضل. لا لا. Okay.
I think natural polymers perform studies. I would like to see if products will go where in the application, in the space, or something like that. I didn't get an idea. What I see is only senses and characterization. What kind of characterization lead you to get an idea of application in space, for example, for protein and zinc oxide with and also I was astonished with the percentage of the filling. 50% is too much. Because it's still stable. The polymer is 50% of zinc oxide or lithium oxide or whatever. It's too much for the polymer to be really stable. So you have an answer.
As I mentioned, I using different concentration to achieve my aim of our work, especially the thermal stability. This percentage was the best for this aim, especially thermal. According to the space environment, we have to prepare a material anti-corrosion, have a lifetime to get the mission I need from it.
Mm-hmm.
So
it's a little bit working under extreme conditions. So normally you are completely right, but in extreme condition you have to a little bit increase some unusual according to the rule of chemistry. I hope so.
And sorry, I may give a hint here. She talked about weight percent. If you right. If she will change to volume percent, I think it will be very, very small. Right. I think. Maybe right or maybe wrong.
It's only because I didn't see the TGA for zinc oxide itself. I compared zinc oxide with the polymer.
Yes.
And the polymer itself is degradable. So what's the effect of zinc oxide when you increase the percentage of zinc oxide? You decrease, of course, the percentage.
The degradation of zinc. Degradation, right.
That's usual. we should, I mean, I'm interested in the applications. Really can stand the temperature, higher temperature without degradation, but in a real application, we have some results.
This is the first job for this application because I hired in the National Research Institute from 2 years ago. I keep up the result for applications.
I think we can continue our discussion in the break time. We have 1 hour for break. It's upstairs. Thank you to all of you, and we continue our discussion. شكرا جزيلا. Thank you.
Molecular Modeling and Molecular Spectroscopy Group at National Research Center. Molecular Modeling and Molecular Spectroscopy is a group at Spectroscopy Department, Physics Division, National Research Center, Egypt. The unit is providing professional technical consultations in molecular spectroscopy and designing molecular models for wide areas of applications. As society engagement, the unit provides training, workshop off and online especially for early career researchers. Among these activates the unit launched Science Cafe. The overall aim is to explore materials to functionalize materials for many applications, which enable the members of the unit to have some projects and awards in many areas in both national and international scale. Moreover, the unit is now collaborating with several research groups and institutes at and outside Egypt. This presentation is going to illustrate the most recent activities of the Molecular Modeling and Molecular Spectroscopy Group at National Research Center. Our goals: providing professional technical consultations and designing molecular models for environmental reactions and electronic properties of matter. Consultations we provide: 1. Designing molecular models especially in the following fields. A. Studying interaction between organic and inorganic pollutants. B. Studying the electronic behavior of many new materials. C. Studying the molecular structure and architecture of many new bulk and nanomaterials. D. Bioactivity of materials that have biological applications. 2. Obtaining the molecular spectra using Fourier transform infrared spectrometer, FTIR. 3. Obtaining ultraviolet spectra. 4. Arranging workshops and tutorials in molecular modeling in collaboration with conference unit of the NRC. Instruments and software available in the unit. 2 workstations and 2 high-speed computers for molecular modeling calculations. Modeling software: Sigres, Gajuain 09, Chemcraft. Purchased from different scientific projects. Instruments: FTIR spectrometer, Vertex 70, Bruker, Germany. UVvis, Carry Series Agilent Technologies. State Award of Excellence in Advanced Technology Sciences, ASRT 2018. State Award in Science and Arts, 1st grade, February 2020.